A very good morning to all of you, and welcome to the first session of third and final day of Virtual Scope 2020 conference. I'm your session chair Subit Kumar, and the session is titled as Nonlinear Optics and NanoPhotonics-I. A few reminders before we start this session. The panelists' pre-recorded presentation will be played, or they can share their live screen using the share screen button at the bottom right of the window. I request all the presenters to strictly adhere to the clock. The audience can use the Q&A widget to type in your questions, as many of which we will be answer at the end of this session. You can use the chat widget to communicate with other attendees and to comment on the presentation. On these notes, let's start the session of nonlinear optics and nanophotonics-I. As a first talk in this session, we have a student talk by Sunil Luhar. He is currently working as a junior research fellow at CSIR CSM CRI Bhavnagar. Without further delay, I welcome Sunil to Spotlight to share his screen for his talk on tunable heterojunction using conducting polymer to photovoltaic application. Over to you, Sunil. Sunil, please unmute.
Yeah. Am I audible? Hello?
Sunil, your voice is breaking. Can I play your video from here?
Hello? Hello?
Sunil, we are facing a little bit network issue, I think. Your voice is...
Hello?
Hello, Sunil. Your voice is breaking. I think we are facing some network issue.
Hello? Am I audible? Now am I audible?
Your voice is breaking, so it can be affect your presentation. So we have a pre-recorded video of you. So can I play your video from here, and you can you can attend the Q&A session at the end of the talk. Shall I do that? Sunil? I think host can play the pre-recorded video now. I think we are facing some network issue to connect with Sunil. So host, please play his pre-recorded video.
Good morning, all of you. Today I am going to present my presentation in SCOPE 2020. SCOPE is a student conference on optics and photonics. My presentation is on tunable heterojunctions using conducting polymer for photovoltaic application. Myself, Sunil Luhar, research scholar at CSIR CSM CRI Bhavnagar. Now I am going to present my presentation on heterojunctions. So what is my objective behind this presentation? So in this presentation I will present motivation for PP heterojunctions. PP heterojunctions is a polyaniline and polypyrrole heterojunctions. So don't go to behind like a PN junctions and like semiconducting junctions. It is a polymer heterojunctions. Then I will describe fabrication step of device, and result and discussion and conclusions or any other questions and answers. So, what is heterojunctions? So, heterojunctions is nothing but when we have two dissimilar materials and junction between two dissimilar material is called heterojunctions. What is that applications? So, applications is a lot of applications behind heterojunctions. So, first of we can make solar cell for using that heterojunctions. So the main problem in heterojunctions research is that how non-conventional semiconductor material can be used to form a heterojunction. The line up of their energy with respect to each other is possible according to band structure. This question has given fundamental approach to this subject, which can go to technologically implications in a various made up of organic substance like conducting polymers. So here I used conducting polymers. It is a pani, polyaniline, and other things is a polypyrrole. So two conducting material I used for the heterojunctions. So why I am using the two heterojunctions? So it is used for sustainable energy, the growth of sustainable energy. Semiconductor used in electronic devices are generally having their fixed band gap. Fixed band gap. It means like generally when we are talking about PN heterojunctions or PN junctions, so it has a like fixed band gap. Like semiconductor material has a fixed band gap like 1.9 electron volt. But I want to tune that energy band gap, so I am using like polymers for tuning the energy band gap. So when it will be tuned, it can captures more energy from sun. So making heterojunctions having a variable rectification property even after its fabrication. So it is a very difficult thing. So I have used tunable heterojunctions device of the conducting polymers. So here it is a SEM image scanning electron microscope. One side I have a deposit pani. It is a polyaniline or it is a polymer, conducting polymer. Other side is a polypyrrole. It is a other polymers, and after that I have recorded to electrochemical state. So it records by parastate instrument. So it give IV curve of the two polymers. So it has JV plots like when we can convert I to J. So it is a minus 200 millivolt to plus 200 millivolt. So what is the fabrication steps for the device? So what I did in that fabrication step, so the device was fabricated using two platinum wires, which were adjusted very close on a Teflon base at a 50 micron distance using a mold and seen by SCM. One platinum wire working electrode was named as a W1 and the other one is W2. Schematic of electropolymerization on custom-made device and SEM image of the heterogeneous device already shown. It is clear shown that sequence is maintained fabricated to the device. As polyaniline over oxidized at a higher potential, so polypyrrole was polymerized first, then pani polymerized and other working electrode. The junction was prepared in a custom-made device consist of two platinum wire. So here you can see how I fabricate my device for solar applications. Now what is the result and discussion? So here I have shown the schematic of growing polymer on W1 and W2. It's a W1 is a one working electron, other W2 is a other electron, other working electrodes. So what thing is here is like two conducting polymers were grown from either side of the device. Polypyrrole is a black and polypyrrole is the black and for color was first grown, and the pani is a green color was grown on other a platinum wire working electron, and heterojunction is formed, which is shown in figure. In SEM image, distinguished morphology of Pani and polypyrrole are clearly shown. So it is PPY grows in a globular like morphology, and Pani is a fibrous like those can be differentiated in SEM image of the heterojunction. Other things is like bend structure of JV plots. So generally, all conducting polymers show multiple band structure at various electrochemical state. Like this property, PPY and PANI also shows various band structures with varying electrochemical potential, which can be seen by spectroelectrochemistry, where UV visible bands shifting continuously observed with the charge of the electrochemical potential. So it is shown in that Pani and PPY band gaps are changing with electrochemical state, which shows the neutral and oxidized state of minus 200 millivolt and 400 millivolt potential. Since this property is reversible, it is possible to fabricate an in situ tunable polypyrrole heterojunctions. A schematic representation of band under various conditions is given in figures, where the relative positions of band energy as a function of electrochemical potential is clearly shown. So the JV plot of PPY and PANI, PPY is the polypyrrole and PANI is a polyaniline. Heterojunction plotted using current density and potential data obtained from experiment at various electrochemical state and pH. Those are shown that at minus 200 millivolt and 0 millivolt ECS, it means electrochemical state, and pH 1 to 4 related curves are given in figure. At 200 millivolt and 400 millivolt related, and again minus 200 millivolt and 0 millivolt plots are given. So the JV characteristics showing various rectification behavior corresponding to different band gap difference value of the polymers. So value of the corresponding rectification ratios are different. So electrochemical states of the polymer and rectification ratio will given like next slide maybe. Yeah. So it is a effect of pH on rectification ratio and JV plots of polypyrrole and PANI. So as it is already said that the band structures are tunable for PPY and PANI. So conducting polymer has a electrochemical potential changes at lower electrochemical potential minus 200 millivolt and 0 millivolt. PPY remains in neutral form at a higher potential values like 200 millivolt and 4 mil. It is oxidized from bipolaric form. Generally, PPY shows a series of absorption spectrum in its neutral form between minus 0.9 volt to 0 volt, and it is oxidized from a higher potential depending upon the applied potential. At 0 millivolt in stage does generally neutral, but when we applied higher potential or lower potential, it will be oxidized. It means it can absorb more light from that sun's. When sun's photons will capture from the platinum wire, then it has relaxation between two electrons will be low. Then it has captured more photons when its conductivity will be like potential will be high or low. So it is minus 200 millivolt and 400 millivolt. But other things we can say, like when pi-pi transition of the neutral pyrrole monomer as we go anodic, it get converted into oxidized form gradually, and 200 millivolt and 400 millivolt corresponding band structure get decreased to 1.4 electron volt. Now effect of pH rectification ratio. So the conductance of both the polymers is depend on pH, and it is interconvertible from conducting to insulator. for both the polymers, in situ conductivity increased by a factor of 10 to power 4 to 10 to power 5 Siemens by changing pH from 7 to 0.8. So it depends what we are doing. So it is already shown in literature, but now we are going to taking like pH from 1 to 4. So the proton doping convert in that polypyrrole to pani, because pani is a conducting, more conducting. So the significant ratio has been observed at pH 1 and pH 2 in less doped polymer with a decrement with increasing pH. In case of minus 200 millivolt, ECS very close rectification ratio value are obtained. At all pH, it means here RR is governed. It means rectification ratio governed by electrochemical state only. So what I have discussed, like conducting polymers as electronic device in situ tunable of rectification behavior at the heterojunctions, demonstration by the example of semiconductor polypyrrole and pani, and have a tunable band gap as a function of their electrochemical state to fabricate in situ tunable polypyrrole heterojunctions. The heterojunction potential state in minus 200 millivolt to plus 200 millivolt and 400 millivolt. Highest rectification ratio was observed minus 200 millivolt, and at a pH 1 where band gap difference of both of the polymers was highest. Identity factor are less than 1 to the less charge carrier recombination in the conducting polymers. The fundamental approach opens door for new possibilities in practical application in electronics. Thanks for patience. It is a first is a pani, another is a polypyrrole. Or thanks for patience is junctions between pani and polypolymer. Now any questions and answer. Thank you.
Thank you, Sunil, for the very nice talk. Now we will take some questions. So, Sunil, I have a question. Sunil, are you there? Sunil, please unmute your video.
Okay.
So your studies you done mainly in acidic pH values, right?
Yeah, it is going to like number of electrons are going to increase. So it deposit on that pani and polypyrrole. Just like it is 3 electrode system, so we can give potential to deposit electrode surface on like polyaniline.
Okay, how your result will vary? I mean, if you go for a basic media, basic pH value, how will be like what kind of effect you will see in this kind of experiments?
Actually, first I have seen that number of number of when number of electrons are going to increase on pani, then band gap is going to increase. Like band gap is going to decrease because of polyaniline get reducing, and polypyrrole is going to oxidize. So number of electrons are going to increase. So I have seen that band gap is tuning between like pH 1 to pH 4.
Okay.
Hello, am I audible? Yeah.
Yes. Okay, thank you, Sunil. If there is no further questions, let's thank the speaker once again. Now we have a last student talk of this session by Ashamoni Neog. So she is currently working as a junior research fellow at the Department of Physics, Tejpur University, India. She'll be delivering her talk on effect of laser power on Raman studies of multilayered WS2 nanosheets. We will be playing a pre-recorded video of her talk, and Ashmoni will be available for any questions. We will start playing the video, playing her talk now. So host, please play her pre-recorded video.
Namaste, I'm Ashamoni from Department of Physics, Tezpur University, Tezpur. Today, the title of my presentation is Effect of Laser Power on Raman Studies of Multilayered WS2 Sheets. Let me move forward. Before going to the details, I would like to introduce a 2D system. We normally know what is 3D system. In 3D system, there are 3 dimensions, X, Y, and Z. And all the 3 dimensions are comparable to one another. For example, Z is comparable here, Z is comparable to X, Z is comparable to Y, and X, Y, Z all are comparable to each other. So that's why it is a 3D system. But in case of 2D system, one dimension is very much smaller than the other 2 dimensions. Here in this case, Z is very, very small than X, Z is very, very small than Y. So that's why it is a 2D system. We normally deal with various types of 2D systems. One is 2D layered materials. In case of 2D layered materials, it is a 2D system, and it is called layered material because these materials are something which can be cleaved along a particular crystallographic direction, which is, for example, when we use a pencil, there is a graphite lead in the pencil, and when we first write with the pencil, one layer of the graphite goes out, and when we write it again, then other layer of the graphite goes out, and so on. This is one kind of example of graphite of 2D layered materials. So there's other several materials are there which are layered materials. For example, transition metal dichalcogenides. Here today I'm interested in WS2. Today I will talk about WS2. That means tungsten disulfide. These are semiconducting transition metal dichalcogenides. This is MOS2, this is WSE2, and this is the MOSE2. So these are popular because they are multi-talented materials, because they can be used everywhere, almost everywhere. They are optically active, so they can be used in electronic devices. They are chemically active, so they can be used in sensors. They can also be used in power generators. They are also good catalysts in some particular applications, and they're also good for spintronic applications, etc. So let me show you some structural details of WS2. So here the tungsten is sandwiched between this sulfur atom. So here these 3 are sulfur atoms, and again these 3 are sulfur atoms, and in the middle of it tungsten is there. So it is for 6-fold coordination. So this is the side view of WS2, and this is the top view of WS2, and this is the representation of 2-layer system. Here this one is WS2, and this one is again a WS2, and they are connected by van der Waals bond. Here it is depicted with dotted lines, and these are covalent bonds. These 2 are covalent bonds. So WS2 is Raman active, so with the help of Raman spectroscopy or Raman spectra, we can get many details about WS2. For example, electron-phonon interaction, transport properties, and with the help of these transport properties, we will get to know whether the material which we are using can be applicable in the electronic devices or not. What is the and the other applications, and so on and so on. So it can also, the Raman spectroscopy can also identify the number of layers in the material, which is huge. So after that, the problem is that temperature can affect the Raman data. That means if temperature increases or decreases, then the peak positions of the phonon modes will also increases or decreases. The size of the peak also increases or decreases, and intensity ratio will also vary. So these are already taken care by many other researchers, but today the problem which I'm going to discuss is that laser illumination can increase the temperature. What I'm saying is that in case of Raman spectrometer, we use one laser source, and we illuminate our material with that particular laser beam, and we get the Raman data out of that. But if we increase or if we change the laser power of that particular laser source in the Raman spectrometer, it can also change the Raman data. It can also affect the Raman data. So that is the problem. So earlier, some people have discussed and investigated this kind of things for other materials, but not for WS2. So here I'm going to discuss this. And what I'm going to study is that how the phonon modes, how the peaks of the peaks corresponding to phonon modes changes with the laser illumination, with the change in the laser power. So to do that, I have synthesized WS2 nanosheets and then did the Raman spectroscopy of those WS2 nanosheets. In order to prepare WS2 nanosheets, I have taken bulk WS2, then I have dispersed those bulk WS2 in a mixture of isopropanol and acetone, and then I have sonicated it, centrifuged it, and dried it to obtain the nanosheets. This is the schematic diagram of that whole process. So after doing the preparation, I have done the characterizations where I have used scanning electron microscope, then powder diffraction system, and then Raman spectrometer and all these things, and I have got some results. Let me first show you the SAM image. SAM image here. So with the help of some some software, I have determined the size or the thickness of these nanosheets, and which I have found to be in between 90 to 100 nanometer. And this is the XRD spectra of WS2. Here you can see that in case of WS2 nanosheets, which is in red, you can see the intensity is very low, and for WS2 bulk, the intensity is very high. You can see the diffraction from 002 plane. You will see the change. So from this we can confirm that whatever we have, whatever material we have made, that we have synthesized, that material is in nano dimension. So after that, I have taken the Raman data. So here you can see that when the power increases, that means from 0.5 to 5, then the peaks positions also changes, and the broadening also takes place. Broadening of the peaks also takes place. So so to do this in more detail, I have taken 4 samples. 4 samples of WS2 nanosheets and done this same experiment. So these are 4 samples. This is 1, this is 2, this is 1, 2, C, and this is D. Here you can see that in the first 3 samples, the positions of the peak, how it is changing. So here, this black one corresponds to E mode. That means E modes represent the vibration of the atoms from left to right, and A corresponds to the vibration of the atom up and down. So here you can see that the positions the peak position changes. First it was low and then high and then again low. Here also it was low, first low, then high, higher than the first one, and then again low. So in this case also this is the same, but in the last case it is not showing the same trend. So here it is not showing the same trend. So this one, this A mode, this a good pattern because it is decreasing, and this also decreasing, this is also decreasing. Here it is not showing that that pattern, but it is something like this. It is not decreasing, but it is it becomes steady here. So from the earlier observations, from the earlier results, which the observations which I have made by other researchers, they have showed if the temperature increases, this peaks correspond to the modes also decreases. So the same thing is happening in this case also. So the results are not that absurd. So we can take this for granted, and we can conclude that even if the exposure time is very small, here I have taken the exposure time to be 10 seconds, which is very less. So even if this exposure time is very small, laser power can affect the Raman data. So in order to establish a concrete relationship between the laser power and the peak positions and the change of the positions, we have to have more data points, and in order to do that, we have to investigate it further. So I have left it for the future. These are my findings, and in order to study various things about WS2 and the variation of peaks, Raman peaks with temperature, I have taken help of many literature, and I'm showing some of them here. These are the references. And then again, I would like to thank my supervisor for letting me to present this, and Department of Physics, Tesla University, and again the Research and Innovation Grant, and then Institution Fellowship. As well as I would like to thank my neighbor Juna Gogoi for letting me in her room so that I can prepare this video. Otherwise, it will be not. It was impossible for me to do this at this point of time. So thank you all.
Thank you, Ashamoni, for the wonderful talk. Now we will take some questions. Satyajit have some question. Please unmute. Host, please unmute Satyajit's audio. Satyajit, you can ask question now.
Hello, Subit. Actually, I don't have any question.
Okay. Your hand is raised.
Yeah. By mistake.
It's okay. Any other question? Ashamoni, I have a question. You are taking, you are reading in different laser power level, right? Yes. But you have only 3 data points. So what is the constraint making? Yeah. So my question is, can I complete? Okay. My question is, what is the constraint for taking you from the reading from different laser powers?
Yes, of course. The constraint is that the instrument which we are using here, I have shown in one of the slide. There, the step means steps are like that. Means first 1% of the total power of the laser, then 5% of the total power of the laser, something like that. So that's why that is the main constraint. It is there in the instrument. So we are thinking of means doing it more so that we can get more data points. So that's the constraint.
So how we are going to solve this in future?
Yes, yes. Means there are many other instruments where we can use, means so we can change this laser power, and we can also do it of our own. Means we have to introduce something in that instrument so that we can change this the laser power continuously, or we can just decrease the step of that laser power. So uh, so that's what we are thinking of.
Okay, thank you, Ashamoni. Let's thank the
Thank you so much.
Okay, let's thank the speaker once again. With this with this talk, we conclude this session. I want to thank all our speakers for their time and participation. I thank everyone in the audience for being here and asking questions. So now next we have a poster session. I request everybody to check the poster session schedule from Scope 2020 website and join the Google Meet by using the link given in the poster schedule. Thank you all.
Thank you.
This meeting is being recorded.
their live screen by using the share screen button at the bottom right of the window. I request all the presenters to strictly adhere to the clock. The audience can use the Q&A widget to type in their questions, as many of which will be answered at the end of the session. And you can also use the chat widget to communicate with other attendees and to comment on the presentations. On these notes, let's start the session of nonlinear optics and nanophotonics by using the share screen button at the bottom right. First, we have invited request all the presenters to strictly adhere to the clock. The audience can use the Q&A widget to type in their questions, as many of which will be answered at the end of the session. And you can also use the chat widget to communicate with other attendees and to comment on the biophotonics presentations. Today he will be delivering his talk on. Let's start the session of nonlinear optics and live screen by using the share screen button at the bottom right. First, we have I request all the presenters to strictly adhere to the clock. The audience can use the Q&A widget to type in their questions, as many of which will be answered at the end of the session. And you can also use the chat widget to communicate with other attendees and to comment on the biophotonics presentations. Today he will be delivering these talks on. Let's start the session of nonlinear optics and live screen by using the share screen button at the bottom right. First, we have I request all the presenters to strictly adhere to the clock.
Thank you.
The audience can use the Q&A widget to type in their questions, and as many of which will be answered at the end of the session. And you can also use the chat widget to communicate with other attendees and to comment on the biophotonics presentations. Today he will be delivering these talks on. Let's start the session of nonlinear optics and live screen by using the share screen button at the bottom right. First, we have I request all the presenters to strictly adhere.
In optics. Right, so this is a quick outline of what I would like to talk about. First, I would like to talk about nonlinear optics and doing nonlinear optical studies at the focus of a microscope, and then using that to do imaging. And the kind of samples we are interested in are going to be dielectric nanostructure arrays in the form of silicon nanodisk arrays. Another synonymous name by which it's also being referred to these days is dielectric resonant metasurfaces. And then I will go on to talking about 2D materials, a little bit about their nonlinear optical properties, and some of the work we have been doing in this space as well. And then, if time permits, the last part of my talk, I'll talk about combining 2D materials with some of these metasurfaces to essentially realize structures where one can enhance nonlinear optical properties of 2D materials by essentially coupling them to a cavity made of these resonant metasurfaces. So the main aim of a lot of the work we do is to do optical microscopy of our samples, and not just any ordinary optical microscopy, but then nonlinear optical microscopy. So what do I mean by nonlinear optical microscopy? Essentially, what is done is that the light, the incident light, let me get a pointer. Yeah, so the incident light, which is shown in red here, which could span visible to near IR, it could even span mid IR also, but here I've shown only 700 to 1700 nanometers. And these are typically pulsed lasers with a lot of peak power. And these are essentially focused using a high numerical aperture objective lens onto a sample of interest. The sample could be biological samples, it could be nanostructures, it could be 2D materials, anything, right? But the idea being that you focus the light very tight on the sample, and at the focus, you create high enough intensities that one can observe nonlinear processes, right? So the polarization of the sample can be written or expanded out into different terms, which could be linear in electric field, which is just your regular linear optical effects, or it could be non-linear in electric fields, depending on the square of the electric field or the cube of the electric field, which we would refer to as second order or third order nonlinear processes. And typically, the wavelengths we are interested in are essentially upconverted wavelengths, where we essentially detect in the visible range by using photomultiplier tubes. So a couple of slides later, I have a schematic of our experimental setup where I would go into a little bit more detail about the kind of experiments we do. Right. So again, to motivate the importance of doing nonlinear optics, so this is an image which is taken from the company Newport's website, where they compare a linear optical process and a nonlinear optical process. So what you see here is that the focus of a microscope, if you were to study a linear optical process, in this case, it's essentially fluorescence, and you see the fluorescence signal being emitted all over the sample cuvette. Right? But then if I were to look at a nonlinear optical process, since it depends on the strong intensities which are being achieved at the focus, this is highly localized. So you see that spot present only at the focus. So to do this experiment, I would have used a wavelength which is probably twice of what I would use for a linear process. But that doesn't matter, that you still get the sectioning capability and resolution as good as a linear microscope by using the nonlinearity in your sample. And one can scan the sample or scan the beam if you want to get spatial information about the sample as well. So what are the kind of nonlinear processes which we would study in such a microscope system? One can study luminescence like fluorescence or luminescence type processes, multiphoton type luminescence processes. So recently there's a lot of interest in brain imaging, where people are interested in 3-photon fluorescence, for example, where one can use wavelengths in the 1700 nanometer, and the 3 photons and the fluorescence of that could be in the visible range. And the advantage is that you get better penetration into the brain, and you can do deep imaging of brain and so on. Right? And similarly, one can do second harmonic generation, where 2 photons, omega 1 and omega 1, can generate 2 omega 1, which is a parametric process where you don't lose any energy to the material. Or one could study 4-way mixing, which is a third order process, where you have a pump and a probe, and you are looking at 2 omega 1 minus omega 2, or mixing terms of that form. One can also look at third harmonic in the same vein as doing second harmonic. The difference being that the second harmonic would require some form of non-centrosymmetry in your material. So a popular example which we also routinely use are these collagen long chain polymers, which have inherent non-centrosymmetry to them, which can be imaged by using a second order process. Third order processes are present in both non-centrosymmetric and centrosymmetric materials, and they do give rise to additional contrast basically in your samples of interest. Then one can also look at vibrational nonlinearities or Raman type nonlinear processes, where the 4-way mixing process can be mediated by vibrational modes of your the sample of interest, that the omega 1 minus omega 2, or in this case omega 1 pump minus omega Stokes, happens to line up with the vibrational mode of the molecule. Then you not only get the nonlinear process similar to a 4-way mixing, but now it is a resonant process because you are probing a vibrational mode of the molecule. And similarly, one can look at stimulated Raman scattering, where one can look at the gain or the loss. You can look at the loss at the pump or gain at the Stokes wavelength, corresponding to the difference being equal to the vibrational mode of the molecule. Right? So these are all the kind of processes one can study in a nonlinear microscope. And in the context of doing the nonlinear studies in the case of 2D materials or dielectric metasurfaces, so far we have mainly focused on these kind of electronic nonlinear processes. And to a large part, we have focused on mainly the parametric processes, though one can also look at multiphoton PL and so on. So this is a schematic of what a typical experimental setup would look like. One would use typically hundreds of femtoseconds or sometimes even tens of femtosecond pulses. And one has to worry about dispersion also, like how do these pulses disperse as they propagate through optical media and so on. So some form of dispersion engineering or prism pairs might be required to compensate for any drawbacks or ill effects of having dispersion. And then what we do is we essentially set the polarization and attenuation by using half-wave plate and polarizers, and then have a suitable galvo scanner to do the beam scanning. And the galvo scanner plane is essentially imaged to the back of this objective lens, so that the beam just pivots rather than sweeping over very large angles and being missed by the objective lens. And then the beam gets focused onto the sample, and whatever is the nonlinear signal, which is shown here in green, is essentially collected in the forward or the backward direction. And we use suitable filters in front, so we selectively detect only the signal of interest and eliminate the strong incident light beam, basically. Right, so this is, I call this our workhorse because this is what a lot of my students use for their PhD work or research work, and this is a very essential part of the kind of research work we do. Right. So if you look at the system, we are not spectrally resolving, like we don't have a spectrometer like to spectrally resolve the wavelengths, but instead we are using a discrete filter, and then we tune the laser wavelength to essentially acquire a spectrum if required. Right. So with that brief introduction about nonlinear microscopy, I would like to move on to talking about some of our nonlinear optical work on some dielectric metasurfaces first. So to give you a motivation for why study nonlinear optical effects in dielectric metasurfaces, I would like to take you back to some of these old examples. So these are extremely old examples of scattering from light particles. So the cup, what you see here is from the 4th century AD, it is present in a museum in London. And similarly, there are also tainted glass or tinted glass, the color stained glass windows, which one would find in old Gothic churches and so on. Right? If we were to zoom in and try to understand what is happening here, what is giving rise to these vibrant colors, it's really scattering from some kind of nanoparticles. It could be metallic, it could be dielectric, right? Like for example, another good example would be titanium TiO2 nanoparticles or microparticles are essentially used in paint, right, to give vibrant colors and so on. So all that is fairly well known, basically. But the interest comes in is can we engineer the scattering spectra of these particles is what is of interest. So if you dive a little deeper into what is giving rise to scattering, it's some form of light interaction with the particle. How do you model it? You can model it in different regimes, right, depending upon how the particle size is when compared to the wavelength of interest. If the particle size is very small when compared to the wavelength, one can come up with a Rayleigh scattering type model. If the particle is comparable to the wavelength, slightly less than the wavelength, then the typical model which is used is Mie scattering. Right? These are all approximate solutions to the Maxwell's equations to model scattering processes. And if you look so these are experimental work where people have looked at metallic particles, dielectric particles, and so on, where interesting scattering spectra or peaks are obtained in the scattering spectra. And they are typically attributed to some characteristic resonances in these particles. And in the case of dielectric particles, what is interesting is that they can be resolved into not only electric resonances, they could be electric dipole, electric quadrupole type resonances, on top of which you could also have magnetic type resonances, magnetic dipole, magnetic quadrupole, and so on. And another interesting aspect is that you can have some of these resonances overlap in spectra and interfere locally. In the near field, they could cancel out each other, that they wouldn't give rise to any light emission and so on. So you can create dark states and so on by essentially suitably engineering some of these resonances to overlap. So the message I would like to convey here is that the nanoparticles by itself gives rise to very rich scattering spectra, which one could use to essentially engineer how light would interact with these particles. Right? So if you were to look at metal versus dielectric, I'll quickly, I won't spend too much time here, but then just to again reiterate, if you look at the basic way the light interacts with metal particle or dielectric particle, we would find that the light would want to stay away from a metallic particle, but then light would easily want to propagate inside the dielectric particle, right? So then if I were interested in doing nonlinear optics, by making use of this particle as my media, then using dielectric particles makes sense because I can leverage the nonlinearity of the dielectric particle and at the same time create field being concentrated, or I can concentrate the field inside the particle that I can study enhancement of nonlinear effects from such particles. And one more thing which is different is that the absorption properties of either a metallic or a dielectric particle is very different. In the case of metallic particles, they tend to have an imaginary part of the refractive index, or there could be absorption, or some cases it's also called as ohmic losses as light interacts with these particles. And the consequence of that is that the quality factors generally tend to be lower. But since the field is concentrated in the edges because of surface plasmon type resonances, the field enhancements at the edges can be extremely high. which is what is being used for surface enhanced Raman, surface enhanced fluorescence, and a lot of other processes. But what we are interested in are dielectric particles. One reason being the absorption losses are generally negligible, so the quality factors can be extremely high. Right? If I run a movie, right, typically in a regular seminar, I would show movies being played where I can show the plane wave interacting with a gold particle or a silicon particle. You would find that if I run the simulation or the time domain simulation for the same duration, you'll find that the field tends to linger around a lot more in the case of dielectric particle, or it's just that the photon lifetime is that much more longer inside the dielectric particle that one can create higher quality factor resonances. And another thing is that dielectric particles, the damage thresholds are also generally higher. So we believe dielectric structures in various forms, either isolated or in arrays, are generally interesting to do nonlinear optical studies because of their inherent interesting properties, basically. Not just optical, but they're also the other associated properties like damage and so on. Right? And as we move on to arrays, the physics of these interactions also get very interesting. Right? So what happens is that in the context of arrays, one can look at guided mode type resonances where light, which is incident, can get guided in the transverse direction. Where if you choose the index of your I call this grating because it's kind of an ordered arrangement of nanostructures, and light can interact with this grating in a way that it can couple into transverse modes of this waveguide, and then certain wavelengths can selectively leak out and interfere with whatever was reflected as is. And this interference can give rise to very rich resonance phenomena occurring in these structures. And one can make use of this to concentrate fields inside the structures to realize filters and a lot of other structures. Right? And over the years, there has been different versions of these kind of grating structures, which people have looked at. There are what are known as high index contrast gratings as well, where you would want your gratings to be fairly isolated from your environment. So this could be like suspended silicon pillars, for example, nano pillars you can think of, where it's essentially a high index medium, fully etched high index medium. And these structures, one could in principle explain them based on guided mode effects as well, but they also give rise to a kind of interesting resonance characteristics that people have been studying that fairly extensively. So what are the applications of such kind of structures? One can use these kind of structures to realize filters, right? Here is an example where germanium gratings have been used to realize filters in the mid-infrared wavelength. So the interest there is that typical filters are made of dichroic coatings and all that. Can I replace dichroic coatings with gratings, making them simpler? And these are standard materials like silicon, germanium, and so on, but still achieve good performance in hard to reach wavelengths like mid-IR and so on, is what is motivating this work. The second work you see here, reflective mirrors. So what you see here is essentially a mesh type grating, which is essentially made of silicon. And this is essentially deposited on top of a 3.5 VIXEL laser. And this acts like the top mirror, which provides the feedback. And hence, this is used as the output coupler for this cavity, basically. Right? So there is interest in integrating these kind of structures to realize filters to realize output couplers for laser applications as well. There's also interest in doing fluorescence sensing. Since you have a resonance peak, it is going to be sensitive. It's going to give rise to strong light matter interaction that one could send in light and locally enhance the radiative emission rate and so on of any fluorophores attached to it, that one could use this to do enhanced fluorescence or low sensitivity molecular detection and so on. And last point of interest, which is also of interest to us, is to do nonlinear optics in these kind of structures. So this I would say is like the Mercedes-Benz of doing metasurface work, where people have combined nonlinear effects from resonant nonlinear effects from quantum well structures with plasmonic cavities embedded on top. So you not only get resonances from the cavity or the plasmonic effects, but there is inherent resonance from the way these quantum wells are being designed. So with these kind of structures, people have been able to realize nonlinear susceptibilities on the order of 10⁶ picometer per volt. And then the conversion efficiencies are like 0.08 or close to 0.1%. right? So if you look at the structure, right, this is just a stack of probably hundreds, less than hundreds of microns, basically, right? It's going to be on the order of tens of microns. An engineered array of these structures can give rise to extremely strong so this is in fact second order nonlinearities. So one could realize extremely strong second order nonlinearities with these kind of structures. Right, so that is what is motivating work in the exploring nonlinear effects in these structures. Can we build ultra thin nonlinear optical media or eventually nonlinear photonic devices which can be used for this frequency conversion, wavelength switching, and a lot of other functionalities. Right, and a parallel area of work which has also caught a lot of interest recently is this area of optical metasurfaces, where one not only engineers the transmission spectra but also engineers the phase spectra you can achieve with these kind of metastructures. Right, this is an example of one of the earlier works from Professor Capasso's group at Harvard, where they've looked at these kind of engineered gold nanostructures, where one can engineer the phase profile across this to do beam steering, for example, to do lensing action and so on. And this is not only restricted to gold particles, you can also look at dielectric structures and so on. And traditionally, the term metasurface has been used for these kind of structures, which not only engineer the transmission or amplitude profiles, but also the phase profiles. But over the years, even the resonant cavities, which I have been talking about, the name has transformed to resonant metasurfaces. Or you can even think of it as like a frequency selective transmit array or reflect array, using the same parlance as used in RF for microwave regime. Right. So in the context of doing nonlinear optics in these dielectric structures, I already showed you one example. There are also a lot of other work which have occurred in this field. Like this is an array of silicon nanodiscs. This was done by Professor Yuri Kivshar's group from Australian National University, where they look at specific resonances for these individual nanodiscs. In this context, they are interested in magnetic dipole type resonances, and they create a very strong enhancement in the third harmonic processes coming from this structure. And one can also do a third harmonic generation microscopy by looking at other higher order resonances. In this context, they look at what are known as anapole type resonances, which essentially are dark in the sense that light is not going to be emitted from the structure because of an anapole resonance. But then as you target the anapole resonance with a third order process, the light would strongly be resonantly enhanced and emitted from these structures. And that's what is being probed in this work. So this was kind of the motivation for why we started doing this work. And these are some of the structures we have fabricated here at IAC, where one can look at these kind of nanopillar type structures, which are engineered here to create resonances around the 1550 type nanometer, 1550 nanometer wavelength range. Right? And these are some of the resonances we looked at. There's a lot of electromagnetic FTTD type simulations which go into designing these structures. And one can choose resonances with different quality factors, width of the resonance, and so on. Right? And another thing which is interesting when we study optical microscopy from these structures is that as the incident light angle is varied, the resonance properties of these structures will also vary. Right. So based on that, as so one thing which is probably well known is that if I change the numerical aperture of my objective lens, the angle of incidence also increases because the light is focusing more tighter. So I'm coming in with larger and larger angles. But then at the same time, the grating structure is seeing light at different excitation angles. So the resonance spectra is also going to split. Right? This is an example of one of the very early works on doing GMR resonances in the presence of varying the angle of incidence. And they find that there is a strong dependence on the angle of incidence. What we have observed is that as you go from weakly modulated gratings to strongly modulated gratings, in that context, when we call it as strongly modulated, we refer to it as like fully etched high index structures. We find that the light would want to concentrate itself into more or less the same mode profile, irrespective of the angle of incidence over a given range of angles. So by that, I mean this, as you go to fully etched, high contrast grating type structures made of silicon or germanium, the angular sensitivity of these structures becomes that much more reduced, which is advantageous because if you want to do microscopy coming in at large excitation angles, then one can efficiently excite those resonances or the designed resonance irrespective of the angle of incidence. So that is a criteria which we worry about when we do the design. And another thing is that one can also play with the quality factor of these resonances. You don't want very high quality factors, in which case it makes it that much more angular sensitive, but moderate quality factors, and how is the spectral width of that resonance comparable to the excitation source spectral width is also something of interest, so that we can match them closely, so that one can efficiently excite resonances in these structures by using the right spectral source, basically. Right. So then we did a lot more scattering simulations, angle dependent simulations, and so on. So if you look at this plot, I essentially show the same resonance, a fixed resonance, but at varying angles of incidence. So almost up to 30 degrees, the characteristic resonance dip remains more or less unchanged. This resonance is rather broad, but then we intentionally chose it that way so that we can match it fairly well to our spectral peak and also keep it as angle insensitive as possible. Right. And then one can do third harmonic generation studies in these samples. As we did that, we were able to observe fairly large enhancements in third harmonic when in the grating structure, the 2D nanodisk array structure, when compared to outside the structure. We obtained about 500 times enhancement in these kind of structures. And then one can do microscopy also in our setup. One can image these nanodisks and also look at the wavelength dependence. And what you see from A to D is essentially sweeping in wavelength from off resonance to on resonance to again off resonance, where you see the contrast changing dramatically. But one thing which came as a surprise to us, which we reported in this paper in Optics Letters, is that these structures, which are made up of amorphous silicon, exhibit strong intensity-dependent third harmonic generation process as well. By that, I mean the third harmonic generation process saturates as a function of optical intensity. But then the saturation effect is strongly dependent on where you excite on that sample. So what you see here is that as I increase the intensity from low intensity levels to reasonably high intensity levels, the contrast in the image changes dramatically. Like initially, it's the nanodiscs which are lighted up, and afterwards the contrast is such that only the outside of the nanodisc is lighted up. So what this essentially tells us is that amorphous silicon is first has some nonlinear absorption processes, thermal processes which are happening at high enough intensity, and the way you excite the sample by scanning it is also is going to determine the intensity you ultimately set up in these nanodiscs, and that is going to determine the contrast you can see basically. So this is the first report of such kind of intensity dependent effects in third harmonic processes in such structures. Right. So with that kind of a quick kind of description of the work we did in the case of dielectric metasurfaces, I will quickly move on to talking about 2D materials and some of the nonlinear effects we have been looking at. So I'm not going to give you very elaborate overview of what 2D materials are and so on, but 2D materials are typically material systems which can be easily exfoliated from a bulk crystal sample. By that I mean you can just use a scotch tape, and when you lift the scotch tape up, you will have some transfer of some of these materials, and this can be done in a highly controllable fashion, in that you can get monolayer to multi-layers more or less accurately. And these days, it's not just such kind of transfers which are done. One can even do MBE, CVD. There are a lot of other processes which have come to scale it up to large areas as well. Right? But what is interesting to us to do nonlinear optical effects is that 2D materials exhibit very interesting nonlinear optical properties. First, the nonlinear optical coefficients are very high. When compared to standard materials, silicon, germanium, silica, they exhibit fairly large nonlinear optical effects. And then it's also very interesting because they are van der Waals stacked. It really depends upon the stacking, and also the crystal structure basically is going to determine whether a certain stack is going to give rise to nonlinearity or not. And furthermore, you can for monolayers, one can create strong excitonic resonances, for example, for TMDCs and so on. So there's a lot of interest in excitonic enhancement of nonlinearities and a lot of other interesting effects. So with the advent of 2D materials to do electronics, then optoelectronics, the next natural progression was to do nonlinear optics, and then to study interesting nonlinear effects. So one such effect I show here from a previous paper, where these are just two monolayers which are laid on top of each other, but then they play with the twist angle of these structures. And then what happens is that depending on the twist angle, the emitted SHG signal contrast obtained using an SHG microscope is very different, right? So the way that you can explain it is based on some interference effects happening between the two layers, basically. But these kind of rich effects are very hard to imagine in a material like silicon, for example. But even recently, people are interested in like few layers of silicon or even silicene, and other materials are also coming up. Another area of interest is to combine these with 2D, these kind of 2D materials with nanostructures. So in this case, it's just gold channels which have been etched where 2D materials are transferred. And locally, where you have strong electric fields, that's where you can create strong light matter interaction and so on. Right? So that is also a fairly interesting area of research. I'll give an example of that later in my talk. Right. So the first thing we were looking at, so one of the materials of interest to us was this tin diselenide material. Tin diselenide is an indirect bandgap material. Recently, there's been a lot of interest in using tin diselenide to build detectors by combining them with other absorbing materials like graphene, TMDCs, and so on. Tin diselenide was also fairly unexplored material. So we wanted to first look at its third harmonic generation property. So we essentially made use of a THG microscope to essentially look at the third harmonic generation signals which are coming from this SNSE2 sample. Right. So what you see here is the optical microscope image. So the contrast you see here, or the different colors you see here, is the result of different thickness of SNSE2 layers. And this is also confirmed with the AFM images which are shown in the image to the right. And what we did was that now we have two different photomultiplier tubes. So we can look at the forward THG and the backward THG from this sample. And what the first striking thing we saw was that the contrast was very different in the forward and the backward THG. So that kind of tells us that the way the THG signal was generated and propagating in the forward and the backward direction was very different, or it was highly dependent on the thickness of the SNSE2 layer. So this is something which we were interested in modeling. So I will come to that in a later slide. And another thing of interest was to benchmark this material with respect to some standard material. So in that context, we have been using glass as our standard material. Glass is a well-known third order, like glass fibers are already well known. In this case, we just used a glass slide whose chi3 was fairly well known. Right? And when we try to compare the chi3 coefficient, so we first compared the PMT voltages we were measuring for our SNSE2 sample and the glass sample, it's shown in blue here. The signals were almost like 10 power 4 times stronger from SNSE2. So it was fairly strong. But then glass is also amorphous, that you don't expect nonlinearities to be very high from hundreds of micron thick glass, basically. Right? But then one could essentially trace it back to a chi3, an inherent material property, a nonlinear material property. And when we did the comparison, we extracted a chi3 value for SNSE2, which is given here, 4 times 10 power minus 19. And when we compared this with values published for glass, we found that these numbers are about 1500 times stronger. Right? So so this is just one example of a 2D material. This is a multi-layered 2D material, which is giving rise to strong nonlinear effects. So so there are similar, you will find similar kind of work being reported for like TMDCs and a lot of other materials, graphene and gallium selenide and few other materials, where if you do a direct one-to-one benchmarking with a standard sample, the first thing which is striking is that the nonlinear properties are huge from these kind of materials. So the next question we had was we wanted to explain why we were seeing this different contrast in the forward and the backward THG signals. So to model that, one has to consider the SNSE2 glass as essentially making up a Fabry-Perot cavity, where this SNSE2 layer is sandwiched between air on one side and glass on the other side. SNSE2 refractive index is comparable to silicon, about 3.5 or on that order of 3.5 or 3.4 or something like that, that it's fairly high refractive index when compared to glass or air. So there is going to be reasonably large feedback coming from as light is going to propagate back and forth in this ultra thin cavity. So the question we had was, how do we model the third harmonic generation process from this miniature cavity? The first step towards that is to first model the standing waves, which are set up at the fundamental wavelength. This is fairly simple to do, right? If you know the incident field, you know the respective transmission and reflection coefficients. Since I know the material properties, I know the transmission and reflection coefficients, then I can write it as a standing wave where at any point Z, I have a wave electric field which is going in the forward direction and another electric field which is going in the backward direction, which is what you see here as these two terms basically. Right. So once I know what is the electric field at any point in the structure, I would be able to calculate the third order nonlinear polarization coming from SNSE2. Right. So I essentially take it as epsilon naught chi3 times cube of the electric field inside the cavity. And when I do that math, I find that since there are two different terms, when I take the cube, I end up with 4 different terms here. And what is interesting here, is that a typical forward THG process, for example, will have only this term, where 3 photons at the wave vector K1 will be interacting with the third order photon at wave vector K3, basically. But what is unique here is that since we have Fabry-Perot feedback happening, you also have backward THG which is being generated. So the backward photons, backward propagating fundamental can give rise to forward propagating THG as well, but that will be highly phase mismatched. But then the other two terms are even more interesting. You could have essentially 2 photons of fundamental going forward, 1 photon of fundamental going backward, interacting with 1 photon of third harmonic going forward. And similarly, you can have the other combination as well, right? So those are more likely to be phase matched just because of the consideration like how these wave vectors add vectorially. You would end up with these terms having a lower phase mismatch, basically. Right? And these terms are fairly interesting and show up only in such kind of cavities. You wouldn't expect to see it in a waveguide, for example. And then once we know the nonlinear polarization, we can set it up as a coupled wave equation and then solve for the wave, the third order wave, third harmonic wave, or the mode coefficient, which is propagating in the forward and the backward direction. And we can write it out in terms of, again, standing wave patterns and so on. Right? So that is kind of a quick overview of the kind of math which goes into modeling these kind of miniature Fabry-Perot cavities made of 2D materials. And once we do this kind of modeling, we are indeed able to explain why we see such discrepancy in the contrast between the forward and the backward going waves, the THG signals, which was very interesting. And this was the first time the forward nonlinear processes were compared with the backward nonlinear processes. So typically you would find papers where a lot of papers where these kind of the backward signals are reported, but they have not been presented with direct comparison with forward nonlinear signals and so on. Right. Another area of interest to us has also been to look at nonlinear effects from heterostructures. Right. In this case, we looked at a monolayer of MOS2, which is sitting on top of a multi-layer SNSE2. And the motivation here is that can I enhance absorption in the MOS2 layer by having a bottom layer of SNSE2, right? The actual physical mechanism by which the absorption is enhanced is by a non-radiative energy transfer process where maybe there will be a small fraction of energy which is absorbed in the MOS2 layer, but whatever is not absorbed essentially will propagate through to this SNSE2 layer. And what happens is that if the energy of the photon is chosen carefully, you can have a significant absorption happening in this SNSE2 layer. And what we observed is that there is a fast energy transfer process by which this energy can be given to the MOS2 layer by a fluorescence resonance energy transfer process. And this was studied by using 2 different mechanisms. The first one was to do it using a linear process. This wasn't built, so the eventual goal is to essentially realize detectors where you separate an absorbing layer from your actual layer, where MOS2 layer, where you would put the electrodes and so on. But in this context, we were using linear process to essentially look at the photoluminescence coming from MOS2. And the enhanced photoluminescence did indeed show us that there is a strong energy transfer which is happening from SNSE2 to MOS2. And then we extended this same work to do 2-photon type excitation as well, where one could come in with 2 photons, where now you can essentially the interest here is that one can have detectors which are capable of detecting photons with energy lower than the band gap by leveraging this to kind of 2-photon process and enhancing that by having it absorbed in the SNSE2 and quickly transferring it to an MOS2 layer. And in this case, we obtained a 7.5 times enhancement in photoluminescence. But the eventual interest here is that can we realize detectors working in the near IR or even longer wavelengths by making use of such kind of processes. So the last part of my talk.
Sorry to interrupt you, sir.
Yes.
You have only 4 minutes left.
4 minutes. Yeah. Quickly, I will wrap up. So the last part of my talk, I would talk about nonlinear effects where one would combine 2D materials with metasurfaces, right? The interest there is that can I leverage the nonlinear effects properties, the strong nonlinear properties of 2D materials, but at the same time enhance them by setting them up in a cavity, right? One could think of various different architectures to do this kind of cavity 2D material arrangement. But what is interesting is that if your cavity is a simple surface pattern, then it makes life that much more easier. Right? So we went on to kind of design some of these resonance structures and so on. I will skip the details, but just to show you, like in this case, we one of the objectives was to realize polarization independent structures. So we realized 2D nanopillar type structures. But what was interesting as we did this work was that you also create depolarization in these structures. If you excite with an EX component, you end up with EX, EY, and a little bit of EZ also. So all these three have to be considered when you calculate nonlinear polarization and so on. So that was one interesting offshoot of this design. And then we went ahead and fabricated these structures, transferred the 2D materials and so on. And when we did the experiments, we did indeed see that there is an enhancement in the second order process close to the 2D material when the 2D material is very close to the grating structures. We also probed the polarization properties on the grating, on the gratings and off the gratings. And we obtained exactly or very similar polarization properties, which essentially showed that the 2D gratings was the way to go if you want to design polarization independent integration of 2D materials with grating structures. And one point which is interesting there is that where this would come in most handy is that you don't have to worry about carefully lining up your crystal axis to the 2D, the metasurface and so on. You are this gives a lot of freedom in how you place the 2D material on top of the grating structure. So let me conclude there. So what I have tried to explain is nonlinear microscopy technique is extremely useful if you want to do spatial, spectral, and temporal imaging. And in our case, the samples of interest are nanostructures, which we fabricate in the clean room, and 2D materials. Some of the emerging areas where we have been applying this is to probe dielectric resonant metasurfaces. But this field is fairly huge that there's a lot of interest in realizing flat lenses, wavefront shaping, holography, and so on. A lot of interesting research is coming out from that area. 2D materials is another problem, optoelectronics, nonlinear optics, and so on. And the kind of synergistic integration of 2D materials with photonic structures is also very interesting. A lot of interesting activities happening there, which we are also working on. So with that, I will conclude. And all the work is done by my PhD students, MTech students, project staff. So I've listed them here. And also I thank all the funding agencies who have been kind enough to fund this work. So with that, I'll conclude and I'll be happy to take any questions.
Thank you, sir, for this nice talk. Now we can take some questions. Okay, so I want to ask one question. So
yeah, please go ahead.
In the slide where you are explaining the application of metasurfaces to design the filters, so I think you are explaining, yes. We are designing a notch filter kind of thing. So if you want to design yes. some band pass filter and a narrow band pass filter, then how narrow we can go with these kind of metasurfaces?
Okay, so if you want to design band pass type characteristics, one approach people have looked at is this kind of combining multiple resonances. If you have coupled resonance type structures, For example, if you have a high Q and a low Q cavity, right? For most part, you will be over a large spectral window, you will be probing the low Q cavity. And if I carefully engineer the coupling of light between the low Q and the high Q cavity, then within that dip or notch, I could essentially have a strong coupling between the low Q and the high Q cavity. And that kind of coupling, or often it's called as like a phaneresonance or electromagnetically induced transparency or analog of EIT. So such kind of processes can be used to create a transmission peak in a large dip, basically. And this really depends on the quality factor of what you can design. In practice, Q factors on the order of like 10 power 5, 10 power 6 are simulated. But really, when you want to fabricate this, it boils down to the kind of surface quality you have, roughness. Typically, I've seen values like 1,000 type numbers experimentally reported. But then that is more of an engineering issue. I think it's nothing fundamental limiting such structures.
Okay, my second question in the microscopic part. You want to do the microscopy with this meta surfaces. There could be some materials which don't have the Chi2 nonlinearity or Chi3 nonlinearity. Then in that case, I think what you are doing, you are putting these kind of surfaces by CVD and other techniques over that surface, and you are doing the nonlinear microscopy. And similar thing we do in case of scanning electron microscope, where we put some gold coating over the materials, and we can also go to very high resolution. So how this technique is better than that, and what are the how you compare this technique with scanning electron microscopy? How it is better than that?
So the microscopy in our case is just a tool which will essentially let us spatially map the sample, right? It's just a visualization tool. Right. In the context of SEM, the purpose of doing gold coating is to prevent charging effects, so that you can visualize your sample that much more easier. Right. The purpose of our nonlinear microscope is to characterize the nonlinear process we are interested in, basically. If one could think about having gold gratings, for example, or gold, if you can somehow drop cast gold particles and so on. One could probably locally enhance the nonlinear process from the sample, basically. That is also doable, but that relies on plasmonic effects and so on, right? But the application of using gold for SEM and the use of grating structures for nonlinear process is probably very different, right? It's not for resolution improvement; it's more for nonlinearity enhancement.
Got it. Next question is from Anirban. What is the effect of laser pulse duration and spectrum on the second harmonic generation microscopic images? Is it all about efficiency?
Yeah, so the laser spectrum is important because let's say if you choose a very narrow resonance, right, and you use a very short pulse laser with a huge bandwidth, spectral bandwidth, then you're not efficiently exciting that resonance. Only the peak might be exciting the resonance. So there is a trade-off between, like, okay, if you know the laser you have, right? Typically, most labs have, like, let's say 80 femtosecond laser or 100 femtosecond TISAF laser or something like that. If you know the spectral width, then accordingly you could design the spectra, the resonance of the structures you would want to study in a way that they are fairly well matched. Then you can enhance the nonlinearities effectively. Otherwise, you are really underutilizing the spectral power density of your light source, is what I think. I hope that answers the question.
If there are no other questions, then let's thank the speaker once again. Thank you, sir, for this nice talk.
Thank you very much. Let me stop sharing.
Okay. The next talk we have is a student talk by Vandana Parmar. Currently, she is pursuing her MPhil in the Department of Physics, Gujarat University. And today she will be delivering her talk on a title of DFT-based study of chromium titanium sulfide intercalated transition metal Dichalcogenides. I would like to invite Vandana to deliver her talk.
Yes, sir. Hello, sir. Hello,
yes,
sir.
Vandana. You can start your presentation.
Okay, sir. Good afternoon, everyone. Myself, Vandana Parmar. Okay, sir. Can you visible my screen?
No, Vandana, your screen is not visible.
Okay, sir. Actually, sir, screen visible share नहीं हो रही है. Hello, sir.
Okay, we also have your pre-recorded video. Do you want us to play that?
Okay, sir. Means का जो शेयर का बटन है वहां से शेयर नहीं हो रही है मेरी PDF जो है वो.
Okay. Then I think we can play your pre-recorded video.
Okay, sir. Okay.
Hello everyone. Introduction. During recent years, the TMDC materials group 4, 5 and 6 have received considerable attention because of their uses, particularly as electrodes in photoelectrochemical solar cell for conversion of solar energy into electrical energy, as well as photonic devices in various electronic applications. Layered compounds such as transition metal dichalcogenides are interesting material with their own property. Transition metal dichalcogenides are very important as a mother material for intercalation compound. Intercalation means the insertion of guest atom, ions or molecules between the layer of layer compound and the resulting substances produced through the intercalation process are called intercalation or intercalates compound. The central purpose of the intercalation is to synthesize the material that have new functions other than those of the mother materials. The compounds crystallize in quasi two-dimensional layer structure consisting of chalcogens, which are detained together by the relatively weak van der Waals forces. Different atoms may be intercalated into weak van der Waals force with transition metal dichalcogenides formula TX2, and a great deal effort has been made to obtain a new function content. Figure 2.1 shows that the TMDC formula MX2. M is equal to transition metal, X is equal to chalcogen. Here we have used the M is equal to Ti and X is equal to S. TiS2 titanium disulfide. Intercalation of 3D transition metal has also been extensively studied in this work, and quite changes have been observed in electronic properties of host transition metal dichalcogenides depending on the intercalates. The effect of charge transfer from gas 3D transition metal to self-intercalated compound TiS2 has been reported. Figure 2 shows that the intercalation of TiS2. Here we have shown that the Ti atom has sandwiched between two sulfur atoms in TiS2 crystals. In TiS2 structure, the TiS has a weak van der Waals force. Here very weak van der Waals force. Then Cr atom can be easily intercalated in this two layer. Therefore, the above says that CRS bonds are stronger than that of the TIS bonds. We have concluded that in CrTIS2, the electronic properties depend on the intercalated atom Cr. Strong hybridization takes place in states Tr3d, Ti3d and S3p. Titanium disulfide has a very small indirect band gap as a semiconductor. In CrTS2 band structure, energy band lengths are shown in the electronic band structure and the density of state. In the present work, the structural and electronic property of CrTS2 compound have been carried out by adopting density functional theory with generalized gradient approximation. Computational aspects. All the calculations in our computational laboratory we have calculated based on the density functional theory with generalized gradient approximation with a quantum espresso code. All the computations are performed with an ultrasoft pseudopotential. Here we have used the DFT based calculation because it is easy for calculate the structural and electronic properties of the material. We have used the generalized gradient approximation for formulation based on density functional theory. It's commonly used for investigation for the material property. We have calculated the electronic structure of CrTH2 by using the various method of first principles. Result and discussion. First, we have calculated the structural optimization. Figure 6 shows that the crystal structure of CrTH2, the different color atom shows that the different atom sum. The lattice constant is used to calculate the structural properties of CrTH2 as layer with CdI2 type structure. Ti layer is sandwiched between two sulfur layers. The unit cell of this structure includes 4 atoms. Gas 3D atom Cr can be easily intercalated in pure TiS2 in very weak van der Waals attraction between the layers of Ti and S as shown in the figure. In very weak van der Waals attraction in TiS2 compound, gas atom Cr can be easily intercalated. Figure 7 shows that the brilliant zone for the hexagonal crystal structure. In brilliant zone, the high symmetry point of each plane. It is more useful in the calculation of the electronic energy band structure. Second, the electronic properties 2.1 band structure. In electronic properties, the energy band structure, density of state, total density of state, partial or projected density of state, we have calculated. Such properties are calculated using the DFT based formulation. In band structure for a crystalline material, a two-dimensional representation of the energy crystal orbital is called the band structure. In this work, the band structure of CrTH2 are plotted. In the energy band structure calculation, the path of K point is considered at a high symmetry path. The order of such path is gamma mk, gamma ALHA. The energy band structure is plotted energy E Fermi electrovolt versus wave vector K. The band structure are plotted in the energy range minus 10.0 electrovolt to 10.0 electrovolt. We have calculated the energy band structure with spin polarized calculation of said materials. Spin up and spin down band structure are shown in the figure. In figure 8, electronic band structure of CrTH2 with spin up. The valence band and the conduction band are overlapped in the energy range minus 5.0 electrovolt to 5.0 electrovolt. Figure 9 shows that the electronic band structure of CrTH2 with spin down. The valence band and conduction band in spin down calculation is overlap near the Fermi energy level at a point minus 2.0 electrovolt to 2.0 electrovolt. From band are overlapped in, we have concluded that the intercalated compound like CrTH2 has a metallic characteristic. Here the band is overlapped maximum at the Fermi level. According to the spin up and spin down band structure of CrTH2, we have said that the CrTH2 is a metallic material with nature. Density of states. Density of states are drawn. The density of states per electrovolt versus energy Fermi electrovolt. The number of available energy states per unit energy per unit volume is the density of states. From the partial or projected density of states, the contribution from the individual orbital of different materials like sp, d and f can be checked. We have used here the tetrahedral method for integration over the brilliant zone to estimate the dose. Both the spin up and spin down calculation of the density of state is shown in the figure 10. It is plotted in the energy range between minus 10.0 electrovolt to 10.0 electrovolt. In both spin up and spin down energy state are drawn for a different color lines. The density of states density is maximum at 6.0 states per electrovolt at a point minus 5.0 electrovolt. in spin-up dose and 3.5 states per electrovolt at a point minus 4.5 electrovolt in spin-down dose above the Fermi region while a conduction band. The electron density maximum at 1.0 states per electrovolt at a 2.0 electrovolt in spin-up and 1.5 electrovolt in spin-down dose. The dose at the Fermi region is 1.5 states per electrovolt. Partial density of state. In partial density of state, CRTS is drawn in the states of CR3D, TI3D and S2P states like unfilled orbitals. In partial density of state, drawn states per electrovolt versus energy Fermi electrovolt. The CRTS to T dose is shown in the blue color line at spin up and spin down. And CR3D, TI3D and S2P are also so in the different color lines. In PDOS, CR3D and TI3D are mainly contributed to the conduction band, while S2P states are mainly contributed in the valence band. The CR3D and S2P states are strong hybridization, and TI3D and S2P is a weak hybridization. Therefore, we have said that the CRTS2 has a metallic material. Conclusion. From the structural optimization, the guest atom is placed between the interlayer of TS2 from the electronic band structure of CRTS2. One can see the overlapping nature of conduction and valence bands. Therefore, the CRTS2 has a metallic structure with spin-up and spin-down electronic configuration and found different from its different energy of states. Above this, we have concluded that CRTS2 compound have spin polarized configuration with spin-up and spin-down electronic band structure. CRTS2 compound has paramagnetic material in nature. Acknowledgement. We sincerely acknowledge the computational facility developed under DSTP's program from Department of Science and Technology, Government of India, New Delhi, India and financial assistance under DRSF2 from University Grant Commission, New Delhi, India. We also acknowledge my guide and our HOD for Department of Physics, Gujarat University. Some are the references. Thank you.
Thank you, Vandana, for this nice talk.
Okay. Thank you.
Now we can have some questions.
Okay, sir.
So if there are no questions, let's thank the speaker once again. Thank you, Vandana, once again for this talk.
Okay, sir. Thank you. Okay, sir. Thank you.
The next talk of our session is an invited talk by Professor Giovanni Volpe. Currently, he is a professor in the soft metal lab at the University of Gothenburg, Sweden. His research interests are in the area of active matter, stochastic phenomena, optical manipulation, statistical physics. Today, he will be delivering his talk on deep learning for microscopy and optical trapping. So I will request the host to play his video.
Hello. Can you hear me?
Yes, sir.
Hello. Hi. So you will play the recorded talk, right?
Okay. If you want to present live, you can.
It's better you play the recorder because I don't have it ready. I thought.
Okay.
My name is Giovanni Volpe.
I will be here for
and
questions.
I will try to convince you over the next 40 minutes that deep learning is a very good idea for microscopy and optical trapping. The usual approach to microscopy, optical trapping, and optics and photonics in general is really top-down, which means that one goes from designing. Thank you for this opportunity to present the Student Conference on Optics and Photonics. My name is Giovanni Volpe, and I will try to convince you over the next 40 minutes that deep learning is a very good idea for microscopy and optical trapping. The usual approach to microscopy, optical trapping, optics and photonics in general is really top-down, which means that one goes from designing an experiment or some theoretical idea, try to realize it and characterize it, and finally succeed, hopefully. This is the approach I have always used in my research, which has been focused on optical trapping and optical manipulation, mesoscopic physics, and active systems. However, recently, an alternative approach has come about. This approach is based on data. It's a data-driven approach that relies on machine learning. Here you can see an overview of different machine learning techniques that go from neural networks, here, neural networks of various kinds. So they are dense neural network, convolutional neural network, recurrent neural network, generative adversarial neural networks. But you should not forget that there are also other possibilities in machine learning, which include the genetic algorithms and reinforcement learning, as well as traditional unsupervised machine learning algorithms, such as regression and k-means and self-organized maps. If you want a nice recent review we wrote about the field and its application to active matter, but also to optics and photonics, you can look at this article referenced here. The reason why machine learning has become such a big hit recently is really because machine learning very recently managed to classify images in a very, very efficient way. So this is ImageNet. Many of you, I guess, have heard about it. And in ImageNet, the task is the following. There are many, many images, millions of images, and one has to classify them based on their content, like which images have dogs, which images have cats. And if we go back in time, in 2011, computer algorithms managed to get, made 25% of error, roughly, which means that they got a fourth of the images classified wrongly. But if you look forward in time, and we go to 2012, we see that this number goes down. The classification error goes very, very quickly down, reaching down to a few percent, like 3–4% in 2016. Now you can see that this increase in precision by deep learning is mainly due to the fact that deep learning started using neural networks, and to be specific, deep learning based on convolutional neural networks. By the way, usually when I give this presentation in person, I always ask the audience to guess, if they don't know already, what will be the accuracy of a human? What will be the error you would make in classifying these images? Well, what's your opinion? The answer is roughly 5%. This means that about 5 years ago, machines became better at classifying images than humans. This is what actually started the deep learning revolution. And as part of the deep learning revolution, people started using deep learning in many different fields. And here I will show how we use it in some projects in microscopy and optical trapping. So I will present a few projects. I will present in detail one project on digital video microscopy, which we did last year. Then I will present 4 more projects very briefly, just to give you a feeling for what kind of applications we can think of in machine learning when applying it to the field of optics and photonics. So let's start with the digital video microscopy. First of all, what is digital video microscopy? Digital video microscopy basically is about identifying the position and maybe the properties of particles in a video. So here you can see a video, well, a frame of a video of colloidal particles. And here typically, what we will do in digital video microscopy is to threshold the image so that it becomes black and white, and then extract the centroids of those white spots, and then maybe reconstruct the trajectories, and from the trajectory we can do a lot of statistical analysis. This is pretty straightforward. You see that this algorithm is pretty simple, and surprisingly, even though it has been around for like 30 years, it's still very widely used and very successful. However, things can get very difficult very quickly. A few years ago, we were doing some experiments, and here you see a video from those experiments where you can see passive particles, these like spherical particles. They are polystyrene microscopic particles, and bacteria moving between them, these bright spots, because they are fluorescent. And we wanted to track both the particles and the bacteria to understand how they interact in this complex environment. The problem is that it was not possible for us to track this with standard algorithm. And we tried very, very hard. We spent a lot of hours and weeks and months trying that. So you can see the problem when you zoom in. If you look at the details, is this a particle or a space between particles? Is this a particle or a space between particles? Not obvious, right? Well, the best we could do was more or less this. This was a lot of work, and you see that it's not a very good tracking, and it's over a very small area. The problem is that, well, it doesn't really work as soon as you move somewhere else on the image, or let alone move it to a new video. This took roughly 1 week of work from one student of mine, Aikut, very good student and very talented in digital video microscopy, but that's the best we could do with standard algorithm. That's the time in which we thought, why not explore the possibilities of deep learning? So we decided to try. And here I will just show a very simplified picture of deep learning, just to give you a feeling for how it works. So let's say we have an image of a particle as input, simplified, and we want to track its position. In deep learning, what you will do is to convolute it with filters and get a feature map, and do this with many, many different filters. At the moment, the numbers on these filters are completely random. This is what is called a convolutional layer in convolutional neural networks. Then we downsample the feature maps, mainly to reduce the amount of data we have to deal with, and we combine them with what is called a dense layer in neural networks. So a series of neurons that receive an input, the values of these feature maps, and kind of sum them up in a nonlinear way. And finally, they give us an output, which is the position of the particle. Again, the connections in this dense layer and with the outputs are completely random at this stage. So what we get at the output, it's a completely random number. So it will tell us, for example, that the position of the particle is here. At the moment, this is not usable to get the position of the particle, obviously, but then what we do is the algorithm that trains the neural network. So we measure the distance between the estimated position and the particle. This is the error, and we backpropagate it. So this practically means we adjust this series of weights in order to make the error a bit smaller, and therefore we need to adjust the previous weights to make the error a bit smaller, and we need to adjust the filters to make the error a bit smaller. This means we get a slightly better result. Of course, we have to repeat this many, many times. Practically means millions of times. And eventually, we will have a neural network that is able to tell us for a given input where is the position of the particle. The neural network we actually used in this work was a bit more complex than this, but let's say in substance is very similar. In this case, we have 3 convolutional layers and 2 dense layers, and so it's much bigger, but the idea is the same. Now the problem arises. In order to be able to use the neural network, we must first train it. How do we train a neural network? Well, we need couples of input images and positions of the particle. The problem is that we cannot get that experimentally. because we don't have them. If we had them, we will not need to have a neural network. So what we did, which worked pretty nicely, was to simulate the positions of the images of the particles. The advantage of simulating images is that, first of all, it's very cheap. You can have as many simulated images as you want. Secondly, more importantly, you know exactly the position of the particle. So you can really show the network any number of perfectly known examples. So that's what we did, and we trained the network over some millions of images, simulated images, and well, at that point we had a network that worked perfectly with simulated images, and we were eager to test it on real experimental data. So what we decided to do is to try with an optically trapped particle. So here you can see a particle. This is a video of a physical particle trapped in an optical trap. An optical trap is essentially a focused laser beam, and the particle stays near the focus and keeps on jiggling around the position of the focus because of the Brownian motion. This is what you see here, and you see that the particle is very nice, the image is very good, very easy to track. This is a standard algorithm tracking it. This is deep track tracking it. They both work perfectly. If you look at the trajectories, the one of the standard algorithm and the one of deep track agree perfectly, down to a fraction of a pixel. And we can even quantify with the probability distribution the position of the particle. We can see that both deep track and the standard algorithm produce the same distribution. And here you see the fit, which is exactly what we would expect for an optically trapped particle. Even better, we can even measure the autocorrelation function of the particle position as a function of time, and you see that both deep track and the standard method produce the same result, which fits very well with what we would expect. So what we did next? What we did next is to keep exactly the same particle in the same optical trap. We switched off the LED high-quality illumination. We switched on an incandescent lamp. And we get this video now. So it's a very bad image because the illumination level is much lower. There is a lot of noise, but it's the same particle. So we know that the statistical properties of this particle must be the same. Well, so this is what the standard algorithm manages to do. You see that it's not really tracking the particle well. Deep track seems to do much better. And if you look at the trajectory, well, of course, it's a stochastic trajectory, but somehow the one tracked by deep track looks much more similar to the previous trajectory we tracked in absence of noise. Let's go to the quantitative comparison.
This meeting is being recorded.
Noise. Let's go to the quantitative comparison. This is the fitted probability distribution. You see that the standard method doesn't deliver us anything really useful. It's completely broadened. But deep track reproduces their correct probability distribution. Even better, this is the autocorrelation function in time. And well, the standard method produces something that is essentially white noise. You see that there is a huge peak at 0 time, and then essentially goes to 0. The small peaks that you see there are 100 Hertz, due to the electric grid in Europe, which is at 50 Hertz, which doubles in intensity to 100 Hertz. So it's really tracking the electric grid more than the particle. Deep track, instead, reproduces the autocorrelation function. That's great. And the reason why this is great is because this tells us that subsequent frames are tracked correctly. Deep track is not trained to track things in time, but still manages to reconstruct the time behavior of the particle much better than the standard algorithm. Well, this was all very nice, so we decided to apply it to our original problem, and we can see that we could track the particles very, very well. And even better, we could even train the neural network to track also the bacteria and distinguish them. So it really worked very nicely. And then once you have done a work, you submit a paper, and well, you're happy, you submit, and then it comes back from the referee, and the referee told us, yes, it's all nice and well, but we would like to see an objective comparison of your algorithm to some test that you don't make up yourself. And therefore, we decided to compare it to this paper, the methods employed in this paper. This is a paper called Objective Comparison of Particle Tracking Methods, in which like 20 groups from around the world came together to compare the performance of their methods in particle tracking. So this is one of the tasks that were given in this paper, and you see that essentially here it's about tracking the position of particles for different densities of particles and different signal-to-noise ratios. And here you see the various methods, and you see that last year. And what is also nice to say is that Deep Track is completely free. So we made a nice software package that you can access, again, completely free and very powerful software to apply deep learning to quantitative digital microscopy. Okay, so I spent quite a lot of time on this first example because I wanted to really give you a feeling for a complete project. Now what I would like to give is more a quick overview of other projects we have done with deep learning, and just to give you a feeling for possible application. Maybe something comes to your mind and you decide that you also want to use deep learning in some of your research. So first thing is measurement of anomalous diffusion. I guess all of you know about diffusion, Brownian diffusion. Brownian particles jiggle around because of thermal motion, and they have a very characteristic exponent, while anomalous diffusion occurs whenever there is a system that is probably out of equilibrium or hindered in its movement. So you can have subdiffusion or superdiffusion, and this relates to the mean square displacement of the motion. So here you can see that we have standard Brownian diffusion is the central case, subdiffusion when the exponent is lower than 1, and superdiffusion when the exponent is bigger than 1. These are the corresponding trajectories. And the standard method, obviously, is to calculate the mean square displacement and fit the exponent. What we proposed was to use instead recurrent neural networks. I will not go into the details of what the recurrent neural networks are and how they work, but what we can see here is that when we have very short trajectories, like 32 points, neural networks are slightly better than the mean square displacement. And of course, when the trajectory gets longer and longer, they become comparable. And here you can see an extensive comparison between the exponent estimated using mean square displacement and the one estimated with recurrent neural networks. And you see that they fit pretty well. These are various experimental cases. So you see that there is a good agreement. So it works. This is nice. But the idea is never to use deep learning or machine learning in general to do something you could do with other standard methods. You always want to use deep learning to do something that you could not do otherwise. And in this case, for example, we decided to explore some more challenging situation. For example, here, instead of having a uniformly sampled input trajectory, we have a non-uniform sampling. Well, then there are no standard methods that can do that, but with deep learning, we can calculate the value of the exponent of an anomalous diffusion, even if the trajectory is not sampled at regular time. Think, for example, experiments with the fluorophores that might blink. You might not be able to acquire a regular sampling. Another example that is even more interesting is when you have a time-varying anomalous diffusion, so a particle that changes the exponent over time. Here you see that it goes from superdiffusive, the blue portions of the trajectory, to subdiffusive, the orange portions of the trajectory. There are no standard established method to find the switching point or to characterize such a trajectory. But the recurrent neural network can be trained to recognize the value of the exponent time by time, and he does it pretty well, and the switching point between the two exponent behavior. So this works also very nicely. So you see, we can do something more than what we can do with standard methods. And also in the case of anomalous diffusion, in case you are very interested in that, we have created a competition organized in collaboration with several groups, the group of Maciej Levenstein in ICFO, Carlo Manzo, University of Vic, Miguel Garcia Mac, Polytechnic University of Valencia, and Ralph Metzler, University of Potsdam. And this is a very nice challenge where more than 50 groups around the world are competing to see who can find the best way to determine properties of anomalous diffusion. We just moved into the second phase on the 14th of September, so you are still on time to join if you're interested. And there will be a very nice competition article. And optical forces arise because of the interaction between the incoming field and the particle and the scatter field. Now, the problem is that if you want to calculate them, it's very difficult because we need to calculate exactly the scatter fields, which is a very complex problem. You can imagine why. The particles we want to trap are often in the range of microns, which is exactly the range of the optical wavelengths we use. So we are in the regime in which we have to exactly solve Maxwell's equation for objects that might not be very regular. That's very difficult and time consuming. This is just to show you the equation. So we will have to calculate the electromagnetic field and then calculate essentially Lorentz force with a tensor and then integrate. It's a very expensive computationally process. So what we thought was to instead use neural networks. And here I will show you, So to use a neural network, so to train a neural network to reconstruct the optical forces. How does it work? Well, we input the position of the particle and we get the neural network to calculate the output, the force that the particle is experiencing in that position. Now, here you can see two graphs. This graph shows the error of the method. So you see that the neural network does much better, well, obviously, than the harmonic approximation, where you say the optical trap is just a spring. So it's minus kx, where k is the stiffness constant and x the position of the particle. That does very bad in terms of error because, well, the trap is not perfectly linear. But you can see that you can imagine using interpolation schemes of different sorts. But even the interpolation schemes you can think of do worse than the neural network by a few orders of magnitude. What is even more interesting is that the neural network is very fast. The neural network is basically as fast as interpolation schemes, even though much better in terms of error, and 4 orders of magnitude faster than making an exact calculation of the forces. Again, why do we care about this? Why do we want to have a fast calculation of optical forces? Well, the reason is because this permits us to go and simulate situations that we could not simulate before. As a simple example, think of an optically trapped particle in an optical trap, and which is a droplet that is slowly dissolving, which means that its radius and refractive index are changing over time. And therefore, we have 5 degrees of freedom. So we have the position of the particle, x, y, and z, plus radius, plus refractive index. Now, let's imagine that we have a flow, and we want to calculate how this particle escapes from the flow. Well, to do with the T-matrix, it will take years for the computer to calculate it. So if we want to do that, but we can do that with the neural network. So using the neural network to simulate this problem, then we can see that if the droplet dissolves very fast. This is the kind of pseudo probability distribution, so that the droplet will escape relatively fast. If the droplet dissolves more slowly, the droplet will be trapped on the edge of the optical tweezer for a while before escaping. So we can see this in simulations that we will never be able to do within a reasonable amount of time using the exact theory for the simulation. So again, an example where we can use deep learning to do something more, something we could not otherwise do with standard methods. Okay, to go to a third example, we can think about we need to track where nanoparticles go, and we might want to take a sample of water and be able to characterize what nanoparticles are there. So characterization of nanoparticles is very important. What we proposed very recently is to use a combination of deep learning and holographic microscopy, where we acquire an hologram of nanoparticles, we transform it, track the particles, and finally use the images of these tracked particles with a neural network in order to extract the radius and refractive index. And the beauty of this is that we can do it very reliably and very quickly. So here you see that deep learning approach and the standard approach. And you see that as a function of the number of images, time steps we acquire and we analyze, we see that the deep learning approach within 1 or 2 frames is able to tell us essentially perfectly the radius. With the standard approach, we need many more time steps. Why is this useful? Well, this is useful because you can imagine, for example, having a microfluidic chamber like we do, in which we flow liquid with nanoparticles and we record them for a few frames. So we don't have an infinite amount of frames, and we want to do this as fast as possible to be able to characterize as many nanoparticles as possible. And by the way, you can see that if you do this on many, many nanoparticles, you see that the deep learning approach gives us exactly, very, very precisely the value of the nanoparticle radius, while the standard approach gives us a very broad distribution, this gray histogram. Again, we can do new stuff. We can think of new applications and faster applications thanks to the application of deep learning with microscopy. Okay, so to conclude, I tried to convince you that it's worth looking into using deep learning for microscopy and optical trapping. And I tried to convince you with some example, discussing in depth one example on digital video microscopy, and then a bit more briefly some more recent work we have done. I would suggest you think about possibilities of using deep learning in your research. Always try to think, obviously, whether deep learning is really the best way to go. If you can do something with standard method, you should not look for deep learning. But deep learning can maybe allow you to do things that you will not have imagined possible before. And with this, I would like to just advertise a conference we organize every year. This is the previous year. So it was last August in SPA Optics and Photonics, which should have taken place in San Diego, but was online. But we will have a second edition of this conference next year, organized hopefully in person in San Diego. And I really welcome you to look into that. If you are interested in these topics, comprising optical computing, AI-enabled photonics, biomedical optics, microscopy, neural connectivity, brain imaging, please look into that if it's of interest for you. I could not put the one of 2021 because we have not yet finalized the program committee, so I don't really know who is going to be there, but the conference chair will be there. And finally, this is a picture taken pre-pandemics of my group at the University of Gothenburg, as well as the various funding sources that have given us money to do the research we love to do. Thank you.
Thank you, Professor, for this very nice talk. And now we can take some questions.
Yes.
First question is by Subit. What is the computation time for a fully trained neural network to track the particle?
Yeah, I was just answering on the chat, but essentially it's as fast as the fastest methods. And the reason is because a neural network, once it's trained, it just does some matrix multiplications. So it's very, very fast. So in practice, we could track the optical tweezer example I showed at 700 frames per second, but we didn't try to push the limits. So we didn't try to use, for example, GPU or other things. And that's as fast as it gets also with the fastest methods, alternative methods. What takes time is obviously the training, which was in the order of, for that network on a laptop, something like 3 or 4 hours. But that's done only once.
Okay. I think there are not any questions. So if there are not any questions, then we can just thank the speaker once again.
Thank you.
Thank you for this talk. Oh, sorry, Satyajit want to ask one question. Satyajit wants to unmute.
Thank you, Professor, for a wonderful talk. Actually, I wanted to know that for neural networking, you have to feed lots of data here in terms of images, right? To distinguish from what we want from what we don't want, right?
Yes.
So, is it also true for other physical sources like sound? I have to discriminate sound from the wanted sound from the unwanted noise and all. Is it can be also used for that?
Well, yes, obviously, yes, it can be used also for analyzing sounds. At the end, the sound is nothing else than a time series. So it's not that different from analyzing a Brownian motion if you think about it from the point of view of a neural network. So you can definitely use it to analyze sounds. Of course, even if you want to analyze sounds, then you will need to have enough data in the training set, which means that you have to find a way to either acquire experimentally enough data or to maybe simulate the data so that you can train the network correctly. So that's usually the difficult part.
Okay. Or it can be generalized for such physical systems, like I have multiple quantum states and I want to distinguish. Or I have, like you said, like from images I can distinguish it, or sound I can distinguish. Can be generalized, this algorithm?
I don't know what you have in mind specifically, what you want to do exactly.
Actually, if I have a bunch of quantum states, different,
okay.
And like you said, I want to pick up a particular state from that.
But how do you have the quantum states? You have already
like in terms of photons.
Okay, and you have measured them.
Yeah, measured them.
I mean, you could definitely try. I mean, you cannot. I don't think you can apply exactly the same algorithm or what we developed, but you can definitely train an algorithm to do that, because it should be able to take the output of your measurement of these quantum states and be able to tell you something about what were the quantum states you started from. Of course, the question there is whether it's worth doing it, in the sense whether this will perform better than standard alternative algorithms.
Okay.
Like, yeah, so that's always the trade-off with any machine learning, because it's very popular at the moment, but you have to use it when it makes sense. But yeah, it's worth trying, let's put it like that.
Okay, thank you.
Thank you.
The next question is from Anindya Banerjee. Can a neural network evolve dynamically such that it can be used for a variety of applications? And the follow-up question is, or is it suitable for a specific application for which it can be explicitly trained?
Well, it's a good question. So if I understand correctly, means the question is, well, of course, you can train a neural network and do a very specific application, and then it's fixed. but it's also true that you can make a neural network which is partially evolving with the new data. So you can have a neural network that adapts to new data as it's being used so that it becomes more optimized for the specific application. This can be done in different ways. One of the way in which it can be done, for example, is having a neural network, like, for example, the one I showed for tracking the particles. That can be fixed once forever, but then we can add an extra layer, which can be trained on new data as they come, so that it gets better with the experiment, gets better at doing the task. So basically you have a general algorithm, but then I give it to you and you use it for a specific setup, specific experiment, and gets optimized over time for your specific experiment. That can be done, and it's a good technique. So the answer is you can do both things.
Okay. Professor RPC wants to ask some questions.
So just wanted to know this, you are talking of optical trapping. So nowadays they are trapping atoms also using optical tweezers.
Yes.
This lattice clocks and all. So whether you can train this to trap just one atom in single tweezer, something like that, that will be really very helpful for making these clocks and other things. Or atomic, like neutral atomic computer, neutral atomic computers.
I mean, I guess. So it was a bit broken, the question, so I'm not sure if
I just wanted to know whether this you can train these traps to trap atoms, all sorts of atoms.
Okay.
Suppose somebody wants to trap cesium, somebody wants to trap rubidium, or somebody wants to trap both in different traps. So whether you can train your algorithm so that you can trap whatever atom you want to trap and all.
Yes, as you yeah, okay. So about trapping atoms, yes, I will say that again, you can trap atoms, and you don't need the machine learning for that. So optical tweezers and optical traps that trap atoms exist already, and they work perfectly fine.
You don't need any training, I think, for that.
No, you can get it to work without any kind of machine learning, and it already works. If machine learning can improve that,
if there is mixture.
Yeah.
There is a mixture of atoms, not
yes,
just
and you want to trap selectively. That could be something where it might be worth using it, because then you can learn, the algorithm can learn how to distinguish them and trap selectively. That could be a good opportunity. Also, one thing that could be useful in machine learning.
Because defect dynamics is very important subject. They want to simulate how this lattice defects behave.
Yeah.
And affect the
yeah, definitely. If you have a mixture of atoms and you want to distinguish them and trap selectively, it can be very helpful, especially because in experiments you always have some noise and some biases from the experimental setup. So if you have a neural network or a machine learning algorithm that adapts to these properties of the specific setup, you can really optimize things a lot. I don't personally work with atoms. I work with optical tweezer, but in the microscopic regime. But in the microscopic regime, for sure, that works very well. So you can get much better results for a given experiment when you use something that is more flexible than a standard algorithm for. But it's also true that if you have a perfectly controlled setup, you can do pretty much almost noise-free measurements. In that case, it's not obvious that it would be useful. But again, it's one of those things that should be tried, and it might. But always with in mind the fact that it's not necessarily going to be better than standard algorithms.
Okay.
It's a good point.
Another thing, suppose I train my algorithm to trap polystyrene latex beads.
Yes.
And now I want to go for protein trapping of biological cells. So whether I will have to do some extra training, or same training will help me to trap even biological cells?
I will say you have to retrain it, because the physical properties of the sample are completely different in terms of refractive index, even refractive index, also the stiffness of the particle, not of the trap. It will be different. So I would guess, I've not tried, but I would guess you will have to retrain it. Unless
For
you
all
make
sorts of particles, you have to do retraining. If
yes,
you change the particle, you have to do the retraining or something.
Well, the problem is this: whichever algorithm you use, you have to choose. Either you make a very broad training for a very many conditions, and then you might not need retraining, but this is not as good as it can get. Or you can do a very specific training for the sample that you want to manipulate, and in that case, you will get a very good result. But of course, as soon as you try to do something else, it will not work. So it's a trade-off between these two things. So it depends on if you prefer to have a broad spectrum of samples that you can manipulate, or if you want to have the best possible performance for one kind of sample. So that's the trade-off.
Thank you. Thank you.
Thank you. That's good questions.
Next, Nigel want to ask one question. Neural systems follow complex dynamics. How sensitive and stable are such systems depending upon the noise in the system?
Okay. What do you mean by noise in the system? In the neural network or in the experimental system? I guess in the experimental system. So assuming it's noise in the experimental system, that's actually one of the good things about neural networks in general. Yes, okay, in the experimental system. So if you have noise in your experimental system, neural networks will, in general, from my experience, work better than standard algorithms. And the reason is because you can train them with the noise. So they learn to deal with the noise if you train them correctly. So that's very, very robust, actually. Even actually in the work that I presented about the calibration of the force fields, in that case, we train without any noise, but then we add and we get the algorithm that characterizes the force fields, and that works very well. But then what we tested is what happens when we add noise to the input signal. And what happens is that the algorithm with the neural network is able still to characterize the force fields, even if without retraining with the noise. So it's very, very robust, much more robust than other standard algorithms. So this is not in the preview we have on the archive, but this will be in the paper because it was one of the questions from the referees, so it will be there once the paper is published. So it's a good question. But in general, one of the big advantages of neural networks approaches is that they are very robust to extra noise.
Thank you, Professor, for this nice talk.
Thank you for the invitation. It was a very nice conference.
Thank you, sir.
Thank you. Bye.
Bye, sir. Due to some technical issue, our next speaker is not with us, and we have to go to the last talk of the session. And the next talk is a student talk by Vibhutiba P. Jetwa. Currently, she is working as a junior research fellow in Sardar Patel University, Gujarat, and she will be delivering his talk on structural and electrical transfer properties of SNS single crystal and their application as a self-powered photodetector. We have his recorded talk and we will play for you.
Hello everyone, myself Vibhutiba Jetwa. I am pursuing PhD under guidance of Professor V.M. Pathak sir at Department of Physics, Sardar Patel University. First of all, I would like to thank organizer for giving me a chance to present my work over here. Today I am going to present the structural and electrical transport property of SNS single crystal and their application as a self-powered photodetector. Content of my presentation includes introduction, growth of SNS single crystal, structural characterization like EDX, SEM, and XRD. Then electrical characterization such as high temperature electrical resistivity measurement, Hall effect measurement, thermoelectric power measurement, optical characterization like UV visible spectroscopy, and application as a self-powered photodetector. Then conclusion and plan for future work. First of all, let us start with the motivation. Why I have choose some particular type of material that is known as tin sulfide. That is basically a chalcogenides. Here in this periodic table, I have highlighted that material that is belonging to chalcogenides. Chalcogenides materials have been of the great interest since many decades because of their interesting properties and application in various areas like optical properties and present great potential in optoelectronic, photovoltaic and thermoelectric device. Among these 2D semiconductors, this tin sulfide is one of the promising material for low-cost solar cell technology because of its optimum band gap that is equal to 1.1 electron volt. Tin sulfide is a non-toxic and earth-abundant material. And this chalcogenides material are basically found in the layer type structure where layer can peel off easily so that thickness can be varied due to layer type structure, and this compound offers very interesting anisotropic properties along different direction. This anisotropic behavior become important when device application of chalcogenides are proposed. And these chalcogenides are highly stable against environmental effect, photodecomposition, corrosion, etc. Now, to make this material, we required this ampoule. So, ampoule is made up from the high quality quartz tube having the melting point of about 1500 degrees Celsius. Here I have shown the schematic diagram of ampoule. The tube having internal diameter of 22 mm and outer diameter of 25 mm and the length is 250 mm were found to be more suitable for the growth process. One end of the ampoule was sealed and other end was drawn into the neck and jointed to the another quartz tube to connect it to a vacuum system for evacuation after introducing a source material. Now, to grow the material, we required chemically clean ampoule. So, we have to clean ampoule with the concentrated H2SO4 and HCl, and then ampoule was filled with the concentrated HF, hydrofluoric acid, and heated at 100 degrees Celsius temperature for about 30 minutes in order to make the inner surface of the ampoule slightly rough because it is useful for a better growth of the crystal. Finally, washing was done by water for 8 to 10 times and then clean ampoule was kept into the oven at 100 degrees Celsius for 24 hours to make it moisture free. For the growth process, first of all, we introduced this source material, that is tin and sulfur, were taken into the cylindrical quartz tube and then ampoule was evacuated at the vacuum level of 10 to the power minus 5 torr and sealed. This sealed ampoule was kept in the furnace for the growth process. This is the schematic diagram of furnace. And the fine powder of the constituent element was kept in one end of the ampoule, that is called source zone. Here, the temperature of the source zone is kept at 950 degrees Celsius and temperature of the growth zone is kept at 900 degrees Celsius. And the temperature of both zones were maintained constant for 60 hours. At this temperature, reaction occur among constituent element in the vapor phase and temperature gradient promote the transport of crystal material from source zone to growth zone where it condenses to produce a crystal. And the furnace was finally cooled down to the room temperature with the rate of 30 degrees Celsius per hour. After this, ampoule was carefully taken out from the furnace and the ampoule was finally broken and resultant crystals were collected. In this table, I have shown the growth condition and dimensional parameter of the tin sulfide crystal, where hot zone is at 650 degrees Celsius, cold zone at 900, growth period is 150 hours, dimension I have shown an appearance of a grown single crystal is like a plate and the color of the grown crystal is metallic black. Here, these parameters are affected to the growth process of the single crystals. Then EDX characterization, that is energy dispersive analysis of X-ray. This technique is used for identification of the elemental composition of the specimen. In this EDX, what happens is that the electron beam inside the scanning electron microscope, it is bombarded to the specimen. The bombarding electron collide with the electron of the specimen's atom and knocking some of them out in this process, and the position vacated by ejected inner cell electron is eventually occupied by a higher energy electron from outer cell. To be able to do so, however, the transferring outer electron must give up some of its energy by emitting X-ray, and the amount of energy released by transferring electron depends on which cell it is transferring from as well as which cell it is transferring to. Furthermore, the atom of the every element release X-ray with unique amount of energy during the transferring process. So from this unique energy, we can identify the element. This X-ray has energy which is characteristic of energy difference. The difference between these two cells, it is depend on atomic number, which is unique property of every element. In this way, it can be identify the type of element that exists in a sample. The chemical composition were analyzed by EDX spectra, that is shown in this diagram. Here, from this diagram, we can say that the highly intense peak, the higher peak in the specimen shows the more concentrated element in this specimen. So Sn, that is the tin, that is more concentrated in this element. Here, this table shows the weight percentage of element obtained from EDX and weight percentage of element taken for a crystal growth. From this, we can say that there is no other impurity atoms. Then SEM, that is scanning electron microscope. It is the type of electron microscope that image the sample surface by scanning it with high energy beam of electron. Here, from this same image, we can say that the grown crystal reveals their layered type growth mechanism. From this image, you can say. Then XRD, that is X-ray powder diffraction. This is structural characterization. It was carried out by powder XRD. For X-ray diffraction study, several small crystals were finely grained with the help of an edge-art mortar and filtered through 100 micrometer slave to obtain grain of nearly equal size. When an incident beam of X-ray interacts with the target atom, X-ray photons are scattered in a different direction. These scattered waves may superimpose, and when the waves are in phase, then the interference is constructive, and is out of phase, then destructive interference occurs. This constructive interference results in the diffraction pattern, which contains information about the atomic arrangement within the crystal. Here, from this X-ray diffractogram, we can identify the crystal structure, that is orthorhombic in this case, and the highest intense peak indicate the most preferred orientation of crystal grains. Peak behavior obtained from the diffractogram indicates good crystallinity, and the density of the grown crystals were calculated by this formula. Here, this table shows the lattice parameter and volume and X-ray density that we can calculate, and the value of this lattice parameter X-ray density have been obtained and presented in this table. It is matched with JASI-PDS data. Then electrical characterization, that includes high temperature electrical resistivity measurement. This experiment has been used to study the variation of resistivity with temperature, so we can identify the nature of material. By using this experiment, the resistance of sample has been measured from room temperature to 650 Kelvin temperature in the step of 10 Kelvin. For each step, corresponding resistivity can be calculated. The variation in resistivity were measured in a parallel and perpendicular direction of crystallographic C-axis. The measured resistance as a function of temperature are shown graphically in this figure, and the graph shows that the resistance decreases with increasing the temperature. It shows that material is semiconducting in nature, and the variation in electrical resistivity as a function of inverse of temperature also shown in this graph. And the entire curve divided into three regions, and activation energy has been calculated, that is shown over here, that activation energy parallel or perpendicular to the C-axis. Here you can see see that parallel to C axis activation energy is higher than perpendicular. That is known as the anisotropic property, and this is useful when device application of such material is proposed. Now, Hall effect measurement, this experiment performed to know the carrier concentration present in this material. The Hall effect coefficients and the mobility were calculated by using this formula, and the carrier concentration was found by using this relation. Here, this result obtained from the Hall effect measurement are tabulated over here. From this result, we can say the type of semiconductor is a p-type. Mobility, carrier concentration, and resistivity were calculated. Thermoelectric power measurement. This is widely used to analyze the electrical property of semiconductor. Here, this experiment was performed on a grown single crystal from temperature of 310 Kelvin to 523 Kelvin with the temperature gradient of 5 Kelvin. This temperature gradient generates an electrical potential within it. It provides the determination of carrier sign, density, and the position of Fermi level in a semiconductor. So, from the graph of Seebeck coefficient versus inverse of temperature, here the slope and intercept gives the value of Fermi energy and scattering parameter. The positive value of thermoelectric power suggests the p-type nature of grown crystal. Then Seebeck coefficient, Fermi energy, and scattering parameter are calculated. That is shown over here. Then UV visible NIR spectroscopy performed to know the band gap of this material. So to reveal the optical properties of tin sulfide, we have measured this absorption in the range of 400 to 1100 nanometer. And the spectrum exhibit high absorption in a short wavelength region, which decay rapidly with increase in the wavelength, showing negligible absorption in a long wavelength region. That means it is good for absorption of sunlight. So from this graph of alpha h nu square upon photon energy, the band gap energy estimated from this plot, and it is found to be 1.15 electron volt, which makes it attractive material for photodetector application. It has been reported having band gap in a wide range, varying from 0.9 electron volt to 1.8 electron volt. So from that, we found application as a photodetector. So application as self-powered photodetector to investigate the optoelectronic property of a grown SNS crystal. Photodetector consists of the crystal with silver electrodes was fabricated as shown in figure. Here, crystals is on a mica sheet, and then contact has been taken from the periphery of the crystal, and the photoelectrical property were measured at zero biasing voltage upon illumination of a laser with different wavelength. The photocurrent increase when a laser illuminates the device periodically by turning on and off at 10 seconds interval, is shown in figure, which clearly show the photoresponse property of tin sulfide crystal-based photodetector. Here, this is a pulse for a 670 nanometer, that means red laser, and this is for violet laser. The photocurrent of device increase and decrease with the irradiation of light on and off, which indicate the photoresponse property of tin sulfide based photodetector, and the value of the rise time are observed to be about 1.24 seconds for 395 nanometer laser and 0.43 seconds for 670 nanometer laser. And the performance of device can be investigated by responsivity and detectivity were calculated by following equations from the photocurrent at zero bias. Here, this is the equation of responsivity, and this is for detectivity, where lambda is the wavelength of incident light, IPH is photocurrent that is obtained by I illumination minus I dark, P is incident light power density as it is an effective area of illumination, and E is electron charge. Here, this table shows the performance of SNS crystal-based photodetector. The bias voltage is 0, so it is self-biased. Wavelength of light laser incident is 670 nanometer and 395 nanometer. Then this is the power, 3 milliwatt per centimeter square and 5 milliwatt per centimeter square. Responsivity that has been calculated. Here it is detectivity, then rise time and decay time for different wavelength of light has been shown. Conclusion of my presentation is here this high quality single crystal of SNS can be grown by using DVT, that is direct vapor transport technique. EDX result confirms the absence of impurity in growth crystal. Peak behavior of powder X-ray diffractogram confirms good crystality of grown crystal of SNS. Obtained value of the lattice parameter by indexing the peak of powder X-ray diffractogram confirms that the grown crystal of SNS possesses orthorhombic structure. The resistivity normal to the basal plane and along the basal plane of SNS decreases with increasing temperature, which indicates semiconducting behavior of the ground crystals. Activation energy obtained from the resistivity measurement is in the temperature range of 308 Kelvin to 573 Kelvin. The positive sign of the Seebeck coefficient show that the ground compound has p-type semiconducting nature, and the scattering parameter and Fermi energy have been calculated. The positive value of the Hall coefficient also indicate the p-type semiconducting nature, and obtained value of the carrier concentration for all the material confirms the semiconducting nature of SNS. The band gap evaluated by UV visible spectroscopy is 1.15 electron volt. This result suggests it could be used in a photovoltaic application. And the photo response parameters such as responsivity, detectivity, rise time, and decay time were calculated for self-driven photodetector based on SNS crystal under illumination of the red and violet laser. Future scope, the series of SNSX, SE1 minus X will be grown by using DVT. After synthesis, this material will be thoroughly characterized using a different technique to understand their various properties like chemical composition, structural, electrical, optical, and thermal properties. The analysis of all this experimental result will be carried out in detail to get the exact idea about the characteristic of this material. All this structure will be further investigated in detail to find out the exact potential of the present device in a specific area of electronics and optoelectronics or some other areas. This device will be studied in detail to understand the exact characteristic of interface and its effect on the performance. Thank you.
Thank you, Jetfa, for this nice talk. Now we can have some questions. I want to ask one question. In the application of these single crystals for photovoltaic applications, what is the quantum efficiency, maximum quantum efficiency you have achieved, or you can calculate for this SNS?
Okay. This experiment, I didn't calculate that quantum efficiency.
No, I'm not talking about the experimental efficiency, the quantum efficiency, which is depends upon this the sulfur that is SNS compounds. Like you have material you have chosen, depending upon that, the efficiency which is possible, maximum efficiency which is possible.
Maximum efficiency. Sorry, I don't have any idea.
Okay. So can you go back to if you have slides? Can you go back to your XRD slide?
Okay.
Highest peak corresponding to 400 million daisies. It's just showing the preferred direction of symmetry in the crystal. This kind of plane you have got. It is you can control this kind of symmetries by the method of preparation, or it is dependent upon the material you have chosen, like SNS material.
By the method of what?
By the method of preparation of the crystal, single crystal.
No, there is no control over there. We can't control that. And this is the XRD of the powder material. That is the tiny crystal belonging in that material.
Okay, fine. Got it.
Okay.
Hello. So welcome back to the final session of Scope 2020. So this session is titled Quantum Optics, and we have 3 talks in this session. We will have 1 invited talk, 1 student talk, and 1 alumni talk. So the first talk to be presented now is by an alumni of PRL, Dr. Ravi Kiran Saripalli. He did his PhD from Indian Institute of Science, and then he was here as a postdoc before moving on to Tulane University, where he's pursuing his second postdoc. Ravi is a very good friend, and he's going to speak today on vortex and vector beams in epsilon near zero materials, which is a very interesting topic. As he has informed us, he would prefer Ravi. Can we unmute Ravi, please?
Hi, Anindya. Thank you for the introduction.
Hi. So you want the recorded talk, right? Okay, so Ravi would be like, we have a recorded talk, so we would be playing that for Ravi, and he will be around to answer any questions that you might have for him. To ask your questions, you can type in the Q&A box below or in the chat box, and he would be there to answer all your questions. So now I would request the host to kindly play the recorded video of Ravi.
Hello, everyone. I'm Ravi Kiran Saripalli, currently a postdoctoral researcher at the Tulane University. I'll be talking about the generation of vortex and vector beams through spin-orbit interaction in epsilon near zero film. The work was done under Dr. Gautam Samanta in the Photonics Sciences Laboratory in collaboration with the NanoPhotonics and Metamaterials Research Group in Tecnologique de Monterrey. This is the outline of my talk. First, I'll be introducing certain terms that I've used in my title with respect to the work done, which follows up into the motivation of the work. I'll be talking about the choice of the sample and the source because these are quite important in this present work, followed by the experimental setups and results. So this will be the layout of my slide where I'll be talking about the experimental setup in the top half and the results in the bottom half, followed by the conclusions. Light has angular momentum in the form of spin angular momentum and orbital angular momentum. Over the last 2 days, we have heard a lot about this, and so I won't be going into too much details. But spin orbital angular momentum has 2 degrees of freedom, and you can easily convert your linearly polarized light into circular polarized light by using a quarter wave plate. Orbital angular momentum arises from helical wavefronts, and each photon has LH cross per photon, plus or minus, where L is known as a topological charge. And based on the topological charge, your phase varies in a helical direction or a spirally from 0 to 2 pi in L number of L times in one wavelength cycle. And so we generally use binary holograms to generate vortex beams or beams with orbital angular momentum using spatial light modulators. So when you interfere a vortex beam with a plane wavefront, then you see these fork patterns. The splitting of the forks indicates the charge of the vortex, and the orientation of the fork indicates the sign. So with this, what are vector beams? Vector beams have spatially varying polarization across the spatial profile. And these are formed by the coaxial superposition of orthogonal polarizations with different topological charge and different sign. So for example, if you have such a state where these indicate the polarizations, the left and right circular polarizations, orthogonal polarizations with different topological charges 0 and L. So for L equal to 3, this would be the polarization mapping, and for L equal to 4, this would be the polarization mapping. As you can see, they are vector beams with a varying polarization across the spatial profile. So generating vortex beams and vector beams are of great interest because they have a variety of applications, and you would want to be able to generate these kind of beams in the ultrafast regime as well, whereas your spatial light modulators restrict this because of them having low damage thresholds and as well as a very low wavelength coverage. So to do so, we need to be able to come up with new techniques where we can control the beam's angular momentum and both spin and orbital angular momentum. And so people have looked into spin-orbit interaction, where so far we have considered the spin angular momentum and orbital angular momentum to be two independent degrees of freedom. But in certain light matter interaction, you are able to have a spin-orbit interaction where you can convert spin angular momentum to orbital angular momentum. So, for example, when light interacts with anisotropic medium or inhomogeneous medium, you can observe this. So in anisotropic medium, the disadvantage is that you have to go in with at a very particular angle, and the efficiency is very small. And also you need tight focusing to observe spin-orbit interaction. In inhomogeneous materials, the medium, for example, in metasurfaces and cube plates, you would require very high precision nanofabrication techniques, which are not always available. Spin-orbit interaction has also been observed in isotropic and homogeneous medium, but you would need the beam to be in the non-paraxial regime. That means that you need essentially a very highly focused beam, and the spin-orbit interaction can only be observed in the focal plane. So in 2017, there was a paper where they have theoretically shown that you can have spin-orbit interaction in isotropic homogeneous medium in the paraxial regime. That means you don't need to tightly focus the beam. So, and this homogeneous isotropic medium were epsilon near zero slabs or ENZ slabs. So epsilon near zero is, so according to a simplistic Drude model, the real part of epsilon goes to zero at a particular frequency known as the Plasmon frequency, and the Plasmon frequency depends on the number of charge carriers. So in metals, this Plasmon frequency is very large. But for highly doped semiconductors, for example, Indium tin oxide or aluminium doped zinc oxide, you can have the number of charge carriers such that this Plasmon frequency is brought into the infrared. And we can access these wavelengths in the lab. So there is a lot of interest in how a wave propagates in these media when operated at the Plasmon frequency. Only because the real part of refractive index also becomes zero. And so people have first shown that it tunnels through and experimentally verified this as well. And also at this Plasmon frequency, such materials have shown very high KED nonlinearity as demonstrated in 2016. We'll be focusing mainly in this 2017 work where they have shown spin-orbit interaction. So this is the essence of their work. So they go in with when you go in with a Gaussian beam having a left circular polarization, the transmitted left circular polarized component and the reflected component remains a Gaussian, whereas the right circular polarized component attains a phase of 2 phi. So this phase is, so you generate a vortex beam. This is to conserve the total angular momentum, of course. So this is the wave vector in free space. If K0 is a wave vector and K perpendicular and Kz are the two components. A non-paraxial beam means that K perpendicular is very large. So now KZS is the K vector inside the slab. You would want to minimize this, the Z component of K vector in the slab so that you maximize the K vector perpendicular component inside the slab, which means that you are maximizing the non-paraxial component inside the isotropic homogeneous medium in order to see spin-orbit interaction. So to minimize this component, the imaginary part of zero, we have no control. It is a material parameter, which is absorption. The real part of epsilon is close to zero because we are operating at the epsilon near zero. So you have to minimize this term, which is the K perpendicular or the perpendicular component of the K vector in the free space. So that means if when you are going in with a like paraxial beam in free space and insulating on the beam, it is actually triggering a non-paraxial beam inside the slab, which means that there is a chance of spin-orbit interaction. Or so that is what they've shown here. Delta is a term that essentially quantifies the amount of spin-orbit interaction. So for normal materials where the real part of epsilon is between 2 and 3, you need to incident a non-paraxial beam to observe a large delta. Whereas when the real part of epsilon is 0, as in epsilon near 0 slabs, you go in with a K perpendicular almost equal to 0, which means you go in with a paraxial beam. So this is very different from what we have shown in the introduction slides of what we require for a spin-orbit interaction to occur. So to experimentally verify this paper, the choice of sample and laser source are important. So we have chosen an ITO film of 310 nanometer thickness deposited on a glass substrate. and the carrier charge concentration was about 10 × 21 per centimeter square, which brings the plasmon frequency to about 1240 nanometer. Now, to access this wavelength in the lab, we did a second harmonic generation of a chromium zinc sulfide laser at 2360 nanometer wavelength. So we used a 5% MgO doped PPLN crystal of 1 mm thickness and having different grating period. The different grating period allowed us to tune the wavelength of the second harmonic generation. More details of this second harmonic generation are found in this paper in 2019, which is a paper of the group. So now that we have the source and the sample, this is the setup that we use to observe the spin-orbit interaction. So say we are incidenting the ITO film with a left circular polarized beam. The transmitted beam will have a unconverted left circularly polarized component and a converted right circularly polarized component. So we are filtering out the left circular polarized component and taking only the right circular polarized component, which should have the vortex or a phase 2 phi. And that is what we are observing on the CCD. So when you go in with the left circular polarized beam, you see this donut-shaped beam. And to confirm whether this is a vortex beam, we do interference with the Gaussian to see the fork patterns. So this is a vortex of order 2, which has been split into 2 singly charged vortices, which is commonly the case when a higher order vortex propagates through a turbulent medium. And as you can see, when you flip the polarization from LCP to RCP, the fork patterns also flip. We did this in the transmitted beam as well as in the reflected beam. So for the reflected beam, we tilted the ITO film by about 15 degrees. Next, we did a focusing experiment. So we placed the same sample between two lenses. The first one is a focusing lens of 20 centimeter focal length. And at the focal length, you can see that the vortex power which is generated or the spin-orbit interaction is very small, as compared to when the ITO film is away from the focus. So this means that you are going in with a less numerical aperture focusing, you see much higher spin-orbit interaction, which is similar to the simulation result that they have shown in 2017 as well. So now, after the transmitted beam in the ITO has 2 components, as I said, 2 orthogonally polarized components. The unconverted component has a Gaussian beam profile, whereas the converted component would have a vortex profile. So you have 2 orthogonal polarizations with 2 different topological charges. So now when you coaxially superpose these 2, you can generate these kind of vector beams. And to characterize the vector beams, we used a quarter wave plate and a linear polarizer and a CCD to measure the different Stokes parameters by projecting it into different polarization bases. And so we see that the polarization mapping has of the spatial profile has a different polarization and you are generating a vector beam. So you could see also this kind of lemon and star singularities, which Subit has described in detail in his talk. I won't be going into too much detail. And we can see that the simulation results match very well with our experimental results as well. So we are able to generate vortex beams and vector beams through spin-orbit interaction without the requirement of high numerical aperture focusing in isotropic homogeneous medium. And that is the sense of this work. So we did some power measurements and as expected, which is again consistent with our experimental results. So to conclude, we have demonstrated spin-orbit interaction and hence vortex and vector beam generation using isotropic homogeneous medium without the requirement of high numerical aperture focusing. The efficiency of vortex generation is about 6% at 1190 nanometer, but we expect this to be much larger when we go to the 1240 nanometer as shown by simulation results as well. And we can use this technique for ultra-fast applications mainly because the entire spectrum was converted into the vortex. So, and also the temporal broadening was very small. And also these films have a very large damage threshold as compared to common techniques using spatial light modulators. So with this, I would like to thank you for your attention and I am open to any questions.
Thank you, Ravi, for such a wonderful talk. Now we open for questions. So if there are any questions, you can ask Ravi directly. He's there. Can we please unmute RP, sir?
Yeah, I have unmuted. Hi, Ravi.
Hi, sir. How are you?
I am fine. You went very fast, man. You had time. Anyway, so can you explain homogeneous medium? It's isotropic. So how this spin-orbit interaction is taking place? Slightly non-intuitive. How this interaction is taking place? Something really.
Yes, sir. No problem. So that was one of my starting slides. So I had only 15 minutes. That's why I rushed through the slide. 1 minute. Okay, I'm not able to share the screen, so that's okay.
No problem. Yeah. You can explain in words, then fine. Yeah, just.
Sure, sir. So, like in homogeneous isotropic medium, like even in thin air, people have shown that if you focus a spin polarized beam, like a circularly polarized beam, then you at the focus in the focal plane, you'll be able to see spin orbit interaction. So there is a transfer of your circular polarization into orbital angular momentum. And it's always like when you go in with left circular polarized component, the right circular polarized component will always have the orbital angular momentum of order 2 to conserve the total angular momentum, basically. And if you go in with RCP, then the LCP component will have a vortex of order -2. So this is how it works. So when you have, people have shown this in Q plates, where you can actually, basically plasmonics in the sense that like if you devise these structures, nanostructures, such that they resonate differently for different input polarizations. So you have these V-shaped structures as well. So which react differently to left circular polarized component, to horizontal polarization and right circular polarization.
So that's fine. These are anisotropic. Yours is isotropic, but these are anisotropic. Q-plate and nanostructures, these metasurfaces, they're anisotropic.
So that is so in anisotropic structures also people have understood spin-orbit interaction. So these are the things. So in this work, what we have shown is that without the requirement of high numerical aperture focusing, and not only in the focal plane, but in an isotropic homogeneous medium in epsilon near 0 medium. So these are what we use is a Indian tin oxide film with a plasma frequency about 1240 nanometer, and in the near epsilon regime was all the way from 1110 nanometer to like 1300 nanometer. If you operate in this regime, so then what happens is the real part of epsilon is close to 0. Correct. And so that is what the simulation paper in PRL show, that like the K vector. So if you incident a K vector, which is when you incident a K vector in the paraxial regime in air, it triggers a non-paraxial component inside the film. And so essentially you are having a non-paraxial component inside the film, which allows for a spin-orbit interaction in the isotropic homogeneous medium. Yes. So that is what I've shown in that
even
slide
if you are not focusing tightly, it creates non-paraxial regime. Even if you are not focusing tightly.
We are not focusing tightly. You are going in with a paraxial beam. So, so the K perpendicular is very
because of epsilon near 0, it becomes non-paraxial.
Yeah, it triggers a non-paraxial component inside the film.
Okay, because of epsilon is equal to 0.
Yes.
Okay. That's how you get spin orbit.
That is how you get a spin orbit interaction. So it is again non-paraxiality inside the film, but the advantage being that to have more non-paraxial component inside the film, you have to go in with a paraxial beam outside the film, incident the film with a paraxial beam in the air.
Okay. Yes. So epsilon near 0, it creates non-paraxial.
Yeah,
it converts paraxial to non-paraxial.
Only. Otherwise, it won't work. Yes.
Okay. Fine. Thank you.
Thank you, sir.
Okay, there are no more questions. I have a very short question actually. So you said SLMs are generally like they have a very low wavelength coverage, right?
Yes.
Yeah. So even the epsilon near 0 phenomenon itself is wavelength dependent, right? So
yeah, but we have shown. So we have shown that we have gone in with almost a 50 nanometer beam, and the entire 50 nanometer spectrum was converted. The main advantage is that these films have a very large damage threshold of about terawatt per centimeter square kind of damage thresholds as compared to SLMs. And also when you can use, that is why you can use in the ultra fast regime as well. So, and since you are using very thin films, the temporal width also doesn't broaden much That is what we have shown.
Okay.
So this is the main advantage as compared to SLMs.
And also, are epsilon near zero similar to near zero index materials, or
slightly different? So they come in the same class. So epsilon near zero is a specific class of near zero materials. So near zero can also mean like mu zero materials as well. They include, this is just a subclass of those kind of materials.
Okay, fine. Okay. So if there are no more questions, we will thank the speaker. Thank you, Ravi, for being there. Thank you so much.
Thanks. Thank you.
We will move on to our next speaker, which is the student talk. It's by Abhinandan Bhattacharya from IIT Kanpur. And he's going to talk about measurement of two-photon position momentum EPR correlation. So Abhinandan, if you're there, you wanted us to play the recorded video, right?
Yes.
Okay. So I'll request the host to kindly play the recorded video, and same as we did with Ravi, Abhinandan would be there to have questions at the end of the video.
Hi, I am Abhinandan Bhattacharya, a PhD student from IIT Kanpur, and today I'll talk about measurement of two-photon position momentum EPR correlations through single photon cross-spectral density measurements. And the central takeaway message from this presentation is that the two-photon EPR correlations can be measured by detecting the coherence properties of one of the photons. So let's begin. In SPDC process, we have the pump beam which interacts with a nonlinear crystal, and one of the pump photon gets down converted into the signal and idler entangled photon pairs. And in that process, the energy as well as the momentum remains conserved. Now, if we measure or fix the position of the idler photon and look at the uncertainty in the position of the signal photon, that we refer as the conditional position uncertainty. And the corresponding probability distribution is known as conditional position probability distribution. And we repeat the same measurement in the momentum basis, and we will get the conditional momentum uncertainty. And if the uncertainty product is less than h bar by 2, it is the violation of Heisenberg correlation and the demonstration correlation and significant indication and with this technique is that it involves a lot of loss and resolution issues. More recently, another better technique has been introduced, that is coincidence measurement using EMCCD cameras, where the BBO plane and its Fourier planes are imaged on this camera, and one is to collect a large number of frames. And if we look at two different regions in the frame and find the correlation between them using this formula, and that gives the estimate of coincidence count between these two regions. And from the coincidence count, we can figure out the conditional uncertainties. But this method requires a large number of image accumulation, vast computational post-processing, as well as it is very sensitive with the distances. So the experimental setup needs to be aligned very precisely. Therefore, all coincidence type detections are actually suffering from different practical or experimental issues, and that adversely affect the accuracy of EPR correlation measurement. One good news is that recently the two-photon correlation or entanglement witness has been observed, at least for PO states, by performing some intensity measurement on one of the photons or on one of the subsystems. And these are the examples of that. And these results do show that the intensity-based measurements are doing a better job in terms of accuracy than the coincidence measurements. And this motivates us to address the problem of EPR correlation in that direction. So this is our theory, and it tells that EPR correlation can be measured by detecting the coherence properties of one of the photons. So we start with a pure two-photon source, and this is the two-photon momentum wave function. And this is our prime interest, the conditional probability distribution and the corresponding uncertainty of the signal photon. And now, if this two-photon wave function actually satisfies this particular condition, then the conditional probability distribution maps into this quantity, which we call as the cross-spectral density, or the two-point correlation of the signal part or the signal photon in the momentum basis, and it carries the coherence information of the signal beam only. And the measurement of the cross-spectral density doesn't require any coincidence detection. And since P is proportional to W, therefore, by measuring W, we can figure out the conditional momentum uncertainty. Next, if the wave function in the position basis also satisfies the same condition, then by measuring the position cross-spectral density of the signal photon, we can figure out the conditional position uncertainty. And now we use these two conditions for measuring EPR correlation. And let's begin with an example. So collinear type 1 SPDC process, and this is the two-photon wave function in that process. And this wave function actually satisfies these above conditions, and hence we have these results. And they imply that by measuring the momentum and the position cross-spectral density functions, we can observe or realize EPR correlations without any coincidence detection. And now we present our experimental demonstration for this theory. So this is our experimental setup. First, we start with the position. The BBO plane is imaged into this camera plane through this interferometer. And we use this interferometer to measure the cross-spectral density function. And if we take a careful look, in one of the arms, we have two mirrors. The input field then goes through two reflection and remains unaffected like this. On the other arm, we take two interferograms, one at delta is equal to 0, other one is at delta is equal to pi. And if we subtract them, we'll get the W. So this is the measured interferogram at delta is equal to 0. This is at pi. And if we subtract, we'll get the cross-spectral density function in 2D. Now, if we perform an integration along y direction, we'll get the one-dimensional cross-spectral density function, and which is the conditional position probability distribution experimentally. And for comparison, we plot the theoretical conditional probability distribution. And this blue one is the theoretical curve, and it fits very nicely with the experimental data points. Now we move to the momentum measurement. For that, we image the Fourier plane on the camera plane using this particular lens combination. and repeat the same set of measurements. So these are the interferograms at 0 and at pi. And if we subtract, we'll get the 2D cross-spectral density function. And now, if we perform an integration, that will give us the 1D plots. And we do see a very nice match between the theoretical curve and the experimental data points. Now, if we look at the widths of these two experimental plots, that will give us the measured conditional uncertainties. So these are the position conditional uncertainty and the momentum conditional uncertainty at the crystal plane that we have measured. And this is the measured uncertainty product, which is less than h bar by 2. And it is the signature of EPR correlation and also a witness for position momentum entanglement. And hence, we have demonstrated experimentally EPR correlations without any coincidence detection. Now, one point that we want to emphasize that how good is our experimental technique is in comparison to the established or the existing coincidence-based methods. So let's look at that first from the accuracy perspective. So this is the uncertainty product for our experiment, and this is the experimental number, and this is the theoretical uncertainty product for our experimental setup. And we can see these two numbers are quite close. And to quantify the accuracy, we define this quantity f. And if f is small, that means better accuracy. For our result, it is about 15%, whereas these are the numbers in the literature. And we do find our measurement scheme has improved the accuracy by a very good extent. And also, our result reports the most accurate EPR correlation measurement in position momentum so far. Next point that we want to look is the degree of violation. And it's a very common quantity in the EPR business where one wants to find how much this uncertainty product is smaller than the upper bound 0.5 h bar. And this is the number for our setup, which is our experimental number for our setup, which is 900 almost. And these are the numbers in the literature. And we do find that we are reporting the highest degree of violation or the observation of tightest position momentum EPR correlation. And from these points, we can say that the intensity-based measurements are doing a better job than the coincidence-based measurement in the context of EPR. And now I want to summarize. We have demonstrated position momentum EPR correlation without any coincidence detection. Also, we have reported the most accurate EPR correlation measurement and the highest degree of violation so far. And our presented scheme is not only applicable for the SPDC process, it also works for the four-way mixing process. And last, the scheme requires coherence measurements. So we believe it can be extendable in the other degrees of freedom also. And this points makes the sense that our presented scheme can have wide utility in the applications where one needs EPR correlation. And now I want to thank my collaborators, Dr. Neelkant Meher, a postdoc student in our group, and Dr. Anand Kumar Jha, who is my thesis supervisor, and our group members. And for financial support, IIT Kanpur and DST. And I also want to thank the scope organizers who give me the opportunity to present my work in this platform. And thank you for your attention.
Thank you, Abhinandan, for a wonderful talk. So now we are open for questions. I see there's a question from Dr. Ravi Kiran Saripalli. He's asking that in your interferometer in experimental setup, are not both photons having even number of reflections counting the one in the beam splitter?
Actually, we are doing this EMCC by we are detecting the intensity in EMCC. So whatever.
Abhinandan, we can't really hear you. Your audio is very low.
Am I audible now?
Yeah, it's better. Yeah, it's better. Yes.
So we expect in the EMCCD camera, that both the photons can arrive with the equal possibility, but whatever we'll find at the end, that's basically the sum of the intensities of both the idler as well as the signal photon. So there is no coincidence kind of measurement involved here, or kind of coincidence kind of situation.
Okay. Well, he was asking about the number of reflections actually that do they have the same number of reflections if you count the beam splitter?
Yes.
Okay. So are there any more questions? Okay, RP Singh has a question, yes.
Thank you, Abhinandan. Nice piece of work and nice presentation. So just wanted to know how you will translate the experiment when you want to have time energy entanglement, IPR correlation, or
Okay, so that once so right now I don't have any precise answer for that. So we know how to measure the. So first of all, there is a condition for a pure state that needs to be satisfied. If it is satisfied, then one needs to figure out how to measure the coherence function in the frequency basis as well as in the temporal basis. So if we can measure the coherence function in both the bases, then it is doable. So
because in your conclusion you said that you can apply to other degrees of freedom. So how you? That's why I am asking.
Okay, so I mean that it can be applicable since people can measure the temporal coherence properties. So and if the wave function satisfies that initial conditions, then I think just one needs to figure out how to measure the frequency coherence. So that part at this moment I don't think.
Frequency coherence. What do you mean by frequency coherence? Slightly.
Coherence between the different frequency modes or the coherence function in the frequency base.
Okay. Okay.
So that part at this moment I don't know actually how to measure the coherence property in the frequency base.
Okay, fine. Thank you.
Are there any more questions? I had one small question actually. Can you comment on generally there's everybody tries for this loophole free tests, right? And then when you do the standard coincidence based measurements with SPDC sources, without post selection, it's impossible to get even you cannot go even above 2 in the Bell violations, right? You assume various post selections to even breach that, but without those, if you consider them as squeeze states, then you cannot generally breach that value also. So in your scheme, are there post selections involved, and if yes, how can this be extended to loophole free tests as well?
There's no post selection involved here, but regarding the second question, at this moment I don't think can be extended or not. There is no post selection involved in this process, first of all. But regarding can it be extendable or not, that I need to think.
Okay. One last question from Satyajit. He's asking, in case of coincidence detecting calculation of visibility is required, could we talk about visibility in this case?
Visibility means in what context?
In case of when you do coincidence detection, generally there's some calculation of visibility involved, right? So maximum coincidence, minimum coincidence, you take that difference. In this case, is there any visibility calculation involved?
No, here we are just measuring we are taking two different interferograms and we are just subtracting them, and that gives the coherence function of the individual beams. So there is no coincidence visibility involved in this calculation.
Okay. And okay, one more question is there. Are the photons degenerate in wavelength from anonymous attendee?
Yes. Yes, we put a 810 filter on the top of the tank in the detector.
Okay, Abhinandan, thank you so much for your talk. It was really nice. For our next talk, we have an invited talk from Professor Ryan Glasser, who is an associate professor in Tulane University in the School of Science and Engineering and he works in the field of quantum information and nonlinear optics. So over to you, sir.
Well, thank you so much for the invitation to give a talk at this wonderful conference. Hopefully everyone can hear me. I think I'm unmuted and my video is going. This is the first time I've given a presentation at a conference sitting outside in my front yard, so hopefully all will go well. Let me share my screen with you all. Okay. I also have this open on my phone so that I can ensure that things look like they're working, and they look like they are. Okay, so wonderful. Thank you again so much for the invitation to speak at this conference. I really appreciate it, organizers. Thank you so much. So I'm Ryan Glasser, down at Tulane University in New Orleans, Louisiana. And I'm going to talk to you today about some work in our group involving machine learning to enhance both classical and quantum optical systems. So I'm going to talk about a couple of different projects that we have completed and that are currently ongoing. And please don't hesitate to interrupt me and ask any questions if you have any. All right. So apologies that I can't be there in person today, by the way. I would have loved to, but 2020 is doing what it is, I guess, unfortunately. So, okay, outline. What am I going to tell you about? First, I'm going to introduce extremely briefly a few concepts that probably most people are familiar with, which is why I'm going to go so quickly. Free space optical communications, pretty much classical free space optical communications. Quantum information, super briefly, and machine learning also very briefly. And I will actually introduce some of these concepts as I'm going along and talking about the different projects that we've done. And then I will turn to talking about correcting for turbulent propagation of light by using machine learning and a couple of different setups that we've done. And that really is involving classical light and classical free space communications. And then I'll transition to an experiment that we completed with some collaborators involving the same kind of concepts of correcting for turbulent propagation of light, but on the single photon level. And I apologize for any background noise as there are cars and things driving by, but my 18-month-old baby is sleeping and I didn't want to wake her up. So sorry about that. Right, so turbulence correction of single photons propagating through a turbulent atmosphere and media. And then I'm going to transition a little bit and talk about something pretty different from the previous two topics involving quantum state estimation enhancement with machine learning. And then I will conclude. All right, so before I get into the actual projects, this is without a doubt the most important slide of my talk. And this is the folks that were involved in all of the projects. So here on the left, now Dr. Sanjay Lohani, who graduated in May in our group, has been deeply involved in the machine learning aspects of all of the projects that I'm going to talk about. And he's currently a postdoc in our group. Erin Knudsen performed the free space optical communications experiments that I'm going to talk about, and she is now a postdoc in California. Honor Donachi was involved in the machine learning development for the last topic that I'm going to talk about. And then I would also like to acknowledge our collaborators, Brian Kirby at the Army Research Lab, Sean Hoover, who currently works for NVIDIA doing machine learning, and Matthew O'Donnell, a researcher out at Northrop Grumman in aerospace systems in California. And these folks were not involved in the projects that I'm going to talk about, but are other researchers in our group. And some of you might recognize this fellow right here, Ravi, who gave a talk earlier today, bright and early in the morning, who's a postdoc in our group and jointly in another research group. And he's been doing all kinds of really interesting and great experiments in our lab. And then we have a handful of other graduate students who are not really involved in the work today, but I'd like to say hi to them. Okay, so diving in very briefly, free space optical communications. Probably everyone is familiar with what that means. Really trying to use light to communicate through space, right? Where space is not necessarily vacuum, like satellite to satellite, for example, communications, but really going through turbulence, like turbulent atmosphere, if you're trying to communicate from a satellite to, for example, a ground station maybe, or from a ground station to a boat, or even worse, going through through water, right, through the ocean, if you're trying to communicate down to a submarine, for example. There are all kinds of modulation schemes, and some of those modulation schemes involve, for example, orbital angular momentum states of light, which probably you've heard about during this conference, in fact, and spatial multiplexing. And really, I'm going to concentrate on the stuff that we've done, which involves spatial multiplexing and making use of non-zero orbital angular momentum states of light, which, when propagating through turbulence, any of these states of light can be relatively strongly distorted, right? You run into all kinds of issues when you send light through turbulent media. You can, for example, there's scintillation of the beam that you're sending. The beam might wander. There are fiber coupling efficiency problems that you can run into due to things like beam wander and scintillation at your receiver. And if you're trying to do, for example, things like remote imaging, or again, communicating by multiplexing spatially, you can run into image degradation and things like that. So really what we wanted to do was try to overcome a number of these problems, turbulent propagation, turbulence distorting and messing up your communications protocol. We wanted to try to overcome that by using machine learning. Okay, one of the other big topics that I want to just very briefly mention, and which everybody here is familiar with, is really quantum information science and quantum optics, right? So in my view, quantum information is really the main big picture topic. And then there are a number of subfields, right? Quantum communication, being able to communicate with, for example, light, quantum states of light, securely in such a way that your encryption method is mathematically secure, right? Not just a computationally difficult problem. There's, of course, quantum computing, which has a number of benefits that I'm sure everyone is familiar with, one of which is the ability to relatively easily decrypt RSA and current classical communications encryption standards, right? Quantum imaging, of course, being able to beat the Rayleigh diffraction limit if you're imaging some kind of system. Quantum metrology, for example, LIGO, measuring gravitational waves, right? You can enhance how well you can measure a signal by using quantum states of light, squeeze states, things like that. And then, of course, excuse me, fundamental physics, right? Just like the last talk, which was wonderful, by the way, violating Bell's inequalities, things like that. Okay, the last thing about quantum optics that I want to mention is really that, as probably everyone here knows, we're really in the midst of the second quantum revolution, right? Where now we're not just discovering new and interesting effects that result from the quantization of light when we're talking about quantum optics, but really we're now moving into being able to develop and apply these concepts to actual in practice devices, right? And there was a lovely experiment a few years ago now, where there was quantum communication was demonstrated from a satellite to 2 ground stations by a collaboration between, I believe, an Austrian and Chinese group, where they were able to generate a quantum cryptographic key between 2 pretty significantly separated spatially ground stations by generating quantum states of light up here on a satellite. So that was super impressive, right? Also, I do want to mention, I'm going to show you lots of images, actually, of states that probably look familiar to you if you're familiar with orbital angular momentum. And I just want to mention that by making use of orbital angular momentum, folks have shown really, really impressive data transfer rates in free space optical and also in optical fibers communication systems, right? Thinking like terabit kind of scale systems, right? And these kinds of states of light, structured light, have found really strong uses in both classical and quantum communication systems. And of course, Professor Forbes, who gave a presentation earlier this week, has been really a leader in the field involving these kinds of systems. Okay, the last topic I want to briefly introduce is machine learning. Machine learning is a subset of artificial intelligence, as probably everyone knows. And specifically, I'm going to mention a handful of neural networks that we've developed in order to accomplish some of the things that I'm going to talk about. And these neural networks are computer programs that are loosely modeled after neuronal connections in the brain. I apologize. There's really loud background noise now because a garbage truck is in front of my house. But neural networks are computer programs loosely modeled after neuronal connections in the brain. And what they do is take an input system, and then there are these numbers of neurons which each perform some nonlinear operation on their respective inputs, perform some calculation, and then feed forward their results to the next layer of neurons, right? And here I have schematically shown a fully connected system where each neuron performs its calculation and then feeds forward to the next layer of neurons connected to each neuron in the next layer, right? And then each neuron in the next layer performs some separate nonlinear calculation and feeds forward its result to the next layer of neurons, and so on and so forth until you get to the output layer, where then something is performed, either a classification or some calculation to generate some output result, right? And then hopefully you can hear me better now. And then at the output, we can calculate an error, and then we can maybe feed back and tweak our individual neurons to hopefully improve the accuracy of the neural network or whatever we're trying to have the neural network do. And then so that's it. That's one training cycle, right? And then we do this typically thousands or tens of thousands or hundreds of thousands of times with the hope that we can then feed in something that the neural network has not seen previously, and it will correctly, for example, predict what that input was. And we've developed a couple of different kinds of these neural networks, and it'll become clear what we've used them for as I go on. Okay, what's my time looking like here? Okay, very good. So now I'm going to turn to the first experiment, or the first setup, which is turbulent correction of classical light by using these neural networks. So here is the simple schematic of what we're trying to do, where we have a transmitter, which is a laser incident onto a spatial light modulator. So we have a Gaussian spatial mode of this beam incident onto a spatial light modulator, which we can input a phase mask onto this spatial light modulator such that we can generate really any kind of spatial image that we would like onto our laser beam. And then we shine that spatial mode, that laser light, through turbulence, some turbulent channel. And then afterwards, we have some distorted image, which might look something like this. Here, by the way, here I'm going to be showing a lot of these kinds of modes, which look like petal patterns, which are oscillating or alternating bright and dark spots along a circular ring. And if you're familiar, I'm not going to speak much about orbital angular momentum, but if you're familiar with OAM, these are superpositions of plus minus L states of light, where you have 2L 2L bright spots along your circular region. Okay, so this distorted image here should be a nice circular image with oscillating bright and dark spots, but you can see it's distorted due to having propagated through some turbulence. And then, of course, we have a CCD camera that we detect this with, which has some non-zero dark counts and background noise right on the camera. So you end up with some result that looks like this, where your image is distorted and also pretty noisy. And these are just simulations at this point, by the way. Then what we wanted to do is take these noisy, distorted images and develop convolutional neural network, which takes as its input this noisy, distorted image, and then the goal is to calculate or find a phase map that we might put onto this spatial light modulator such that we have an image that is different now at the transmitter, but when it propagates through the turbulence, you end up with a more ideal, less distorted image after propagating through the turbulence. So we have some examples here where here the target modes are shown up top. So these are ideal without any distortion due to turbulence, just a Gaussian plus minus 2L spatial profile here, 4 spots, however many spots this is, 10 maybe, and maybe 20 spots. And then we have 3 pairs of columns. On the left is the distorted image at the receiver due to turbulence. So here you can see this Gaussian does not look very Gaussian any longer. And in the center is the predicted phase mask due to the neural network upon detection of the distorted mode profile that we should put back onto the spatial light modulator. And then on the right-hand column is the new received image at the receiver after propagating through turbulence. And so you can see it's not perfect, right? This is not a Gaussian exactly, but it's significantly better than this, right? And in this kind of communications paradigm or this communications scheme, the alphabet really is, you know, what is the superposition? What is the mode profile? Is it 1 spot, Gaussian? Is it 4 spot, 2 spots, 4 spots, 6 spots, 8 spots, 10 spots, ... up to 20 spots, right? So that's the alphabet. And you can see it works relatively well for any of these kinds of spatial modes. This would be very difficult to tell how many bright and dark spots there should have been along this ring. And here it's perhaps a little bit easier, right? Okay. So here are just some example. This is simulation work still. Here are some examples of the images up top for increasing turbulence strength. And up here you can see the image. This would be very difficult to classify which plus minus superposition we have, how many bright and dark spots we have. But the corrected image, it's significantly easier to see. And we published this work, which was all simulations, in 2018. So this previous work here that I mentioned suffers from one pretty important difficulty, and that is that you have to feed back to your transmitter, right, to sort of pre-correct for propagation through turbulence. But turbulence, of course, varies with time, right? So really, this would be difficult to implement in a realistic communication system, right? So really what you want is something that is just receiver end only, right? Nothing that feeds back to your transmitter. So that was the next thing that we did. And as I've drawn it here, you might think that there's feedback, but there's not. All the bottom half here is the receiver. I just drew it beneath because it was kind of difficult to fit on a slide if I drew it on the right-hand side. But up top, we have the same kind of transmitter system, turbulent channel, and then our receiver down here. And so we have our noisy, distorted image. Now we've developed a generative neural network, which takes, again, as its input, some noisy, distorted mode profile. And this neural network then generates a new image, which is hopefully denoised by some amount, and also more ideal in terms of the mode profile. So cleaned up and sort of corrected for this distortion. And then this corrected, generated mode profile is then fed into another neural network that we developed, which just serves to classify what image out of the alphabet has it received, i.e. how many spots are there along this ring. And then once the second neural network classifies this generated image, then we can compare it to what was actually sent and calculate. This is an SER, so symbol error rate. It's not just a binary. We're not just classifying bits, right? There's a larger number of letters in our alphabet than just zeros and ones, right? So we can calculate a symbol error rate. And then we can do the same thing without using the generative neural network, right? And just try to classify the received image and compare it to what was sent and see if we can find any improvement when we use our generative neural network. Okay, and there's no feedback There's no adaptive optics, no active control or anything like that. Everything is sort of passive here, right? And at the receiver. So we set up and performed this experiment in our lab. Here is the experimental setup. We have laser, the first spatial light modulator, which generates our image to be transmitted, a second spatial light modulator, which we can simulate turbulence, and then just a variable attenuator to change the signal to noise ratio, and then a camera, which detects the image. And then we have our neural network scheme that we've developed. And here, of course, the experiments always look more complicated than the simple diagrams do, right? Here, this experiment pretty much was on this sort of half or third of the optical table over here, our laser system, and just a bunch of optics, and then detectors and spatial light modulators sort of over in this region down here. Okay, so here is some simulation results with our generative neural network and classifying convolutional neural network in conjunction. Here we have just varied the signal to noise ratio. We have pairs of columns where here we have the received mode profiles. So just a Gaussian, but it's distorted. And then this is the generated image after the generative neural network, right? And then here we're, for example, varying the communication link distance. And you can see that, you know, you have relatively distorted modes and then generated modes. And this is just the schematic of what the generative neural network looks like, and then the classifying convolutional neural network. And we saw that we were able to improve this should actually be SER, symbol error rate, not bit error rate. But nonetheless, we saw a pretty significant improvement in the error rate. So lower is better at lowering the error when we use the generative neural network down here in red, as compared to when just using the classifying neural network in conjunction with the received noisy and distorted images. And we can vary sort of anything you want, right? Signal to noise ratio, communication link distance, things like that, strength of the turbulence, etc. And there's way too much going on this slide, so don't read too much into it. All I'm showing here, or hoping to get across, is that as we vary pretty much anything, you know, communication link distance, signal to noise ratio, stuff like that, we can always see a nice improvement in the error rate. So we get a decrease in the error rate when we use our generative neural network. Okay, here is some experimental data. Here we have pairs of columns again, where we have the received images and then the generated images from the, so C stands for corrected, the images that are generated by the generative neural network. And here we're increasing the turbulence strength. And you can see, you know, this, for example, take this one. This would be relatively difficult for a classification network to tell you how many bright spots there should have been. In here on the generated neural image, it's pretty clear. So on the right-hand side, these two plots are just a measure of error. Here we've used mean squared error because that's what the referees asked us to use, but it's just a measure of error. And here the brown data points correspond to just using the received image, and the lower error, improved error, blue points correspond to using the images that are generated by the generative neural network. And we see an error, an improvement in the error. And this is just as we vary the strength of the turbulence and as we change how strongly we're attenuating at the receiver. So varying the signal to noise ratio. And here we have some pairs of images, which are just correlation matrices showing the, on the y-axis, the transmitted OAM profile, or really superposition profile. And then on the x-axis is what the demodulated, what the receiver tells you it received, right? So ideally, you should have a nice diagonal line here, where if I've received, you know, OAM profile plus minus 5, that indeed that's exactly what I sent, right? And if I say I received 8, then I've received, or I was sent 8, right? And so on the left is without using the generative network, and on the right is with using the generative network. So there's a pretty substantial improvement when using the generative neural network. Okay, so now I'm going to transition to much time. I'm going to transition to the single photon experiment that was performed at LSU in conjunction with Omar's group, the Quantum Photonics Lab. So here's Omar. They're just an hour and some change away down the road in Baton Rouge, and they had gained some interest in the stuff that we were doing with respect to the machine learning, and they have a nice single photon SPDC source and have an intensified CCD camera and single photon counting modules. So they were in a good place to be able to perform this experiment in the single photon regime. So the experiment is pretty much the same as the one that I mentioned previously, the pre-correction, so the feedback to the transmitter experiment, where you have a first spatial light modulator, a second spatial light modulator to simulate turbulence, and then a camera. And they have two sources, right? A classical laser light source, and then they can switch to using their periodically pulled KTP SPDC source, where they can herald on single photons and then use a single photon to be transmitted to the receiver. Okay, so the idea is exactly the same as I mentioned before. Here on the left-hand side, these three columns with the red images are for the classical light with using the Heaney laser. And you can see that the corrected images are nicely corrected for, the turbulent images are in the middle. But here on the right-hand side are the intensified CCD images after counting, measuring single photons over and over again, right? But here you have a nice superposition state of plus minus some L on your single photon. And then, of course, you're taking many measurements, right, to gather this image for your single photons. And then here's the distorted image when the single photons are passing through turbulent media on the spatial light modulator. And then here's the corrected. And again, this correlation matrix for the ideal, the distorted, and then the corrected when using single photons. And of course, we can calculate and measure the density matrices for the single photons in this case. And here up top, we have the no turbulence single photon state density matrices. Here we have the turbulent propagation single photon density matrix that we've measured. And then down on the bottom, the turbulence corrected. And you can see that there's pretty nice overlap between the no turbulence and turbulence corrected density matrices, and probably not so much the with turbulence density matrix. And if we calculate the fidelity, basically the overlap between the no turbulence density matrix and the corrected density matrix, the fidelity is something like 99.8% in the experiment. Lastly, we can calculate the channel capacity, so sort of the information capacity of the photons used in the single photon experiment. And of course, probably folks know that when you use different degrees of freedoms, you can indeed have larger than a single bit of information contained per photon. Here we have in the blue, no turbulence, the information capacity in our single photon. And then in green, the information capacity when we have the turbulence turned on. And then in red, the corrected photon information capacity. So we don't get back up to the sort of ideal case for us, but we get pretty close, pretty significant enhancement. Okay, so now I am going to talk to you, I'm going to switch gears a little bit and talk to you about enhancing quantum state estimation by using neural networks. And so I'm going to switch colors because I'm talking about a different project. And so we published this very recently in a journal, and the title is, I guess, what you would expect: Machine Learning Assisted Quantum State Estimation. And so we did this work in collaboration with a couple of folks up at the Army Research Lab in Maryland. Okay, so very briefly, probably most folks are familiar with quantum state estimation. But quantum state estimation, quantum state tomography, I'm using those phrases to mean the same thing, is really used in order to characterize a quantum system, right? And so what you do typically is you have some system where you generate some quantum state, or you push a button and you hope that you generate some quantum state, right? You need to measure the state that you've generated in order to sort of verify that you've generated the state that you hope that you generate when you push the button on your system, right? And so the way this works typically is by doing quantum state tomography, where if you have, for example, a 2-qubit system, for example, making use of the polarization degree of freedom of light, right? You're trying to generate some HV plus VH kind of entanglement, say. You push your button, you hopefully generate that 2-photon entangled state. Then you need to perform a series of measurements, one at a time, of course. Take the measurement, record the outcome, repeat that same exact experiment by making perhaps a different measurement. If you have 2 qubits, typically this involves 36 measurements for Stokes reconstruction, right? Stokes measurements. Measure these 36 measurements, and then you do this many, many times over and over again in order to gather statistics. And then you run your results, your measurement results, through some algorithm, and then you generate what was my most likely quantum state that I generate when I push that button, right? And it turns out that just the classical computational overhead of this kind of thing scales very poorly with the dimensionality of the quantum system. So, for example, like I mentioned, a 2-qubit optical system requires, typically, if you're doing Stokes reconstruction, requires 36 measurements, and you have to make many of those 36 measurements, right? It turns out it scales very poorly, like I mentioned, and there was recently, 2005, that's kind of a long time ago now, the reconstruction of an 8-qubit state took weeks of computation time. So it took them, I forget how long, maybe a day of data collection, but then weeks of computation time just on a classical computer in order to reconstruct the state that they actually generated. So our goal here was, can we use machine learning and neural networks, hopefully, to help reduce this classical computational overhead in these kinds of state tomography systems? So just very briefly, we indeed we're looking at a 2-qubit system entangled in terms of polarization, right? HV plus VH kind of polarization. This requires 36 measurements, so a 6x6 matrix, and then many of these 6x6 matrices. And we were simulating an off-the-shelf device that you can buy from NuCrypt, which does all of this automatically for you, all of these 36 measurements, and then you can calculate your density matrix of your state that you generate when you push the button. Okay, so what we did was develop a neural network, here just schematically shown, which takes in these 36 measurements, so a 6x6 matrix, these tomography measurements, it takes those as its input, and then its goal is to calculate, hopefully find what the density matrix of the system was that corresponds to these noisy 36 measurement outcomes. What's my time look like? Okay, a few minutes. So indeed, we did that, developed this neural network, and it worked pretty well. So for example, here we have the number of noisy measurements for each density matrix that we're varying. And then we have the average fidelity, which is just, again, right, the overlap of what our neural network, the density matrix that our neural network predicts as compared to the actual ideal noiseless density matrix, so the density matrix corresponding to noiseless measurements. So here is 100% and here is 70%. Without using our neural network, just using the standard Stokes reconstruction, we obtain for mixed states. We did this both for mixed and pure states. For mixed states, the Stokes reconstruction gives you something like this, 7 or 8%. But then using our neural network, we see an improvement up to near unity fidelity. And then similarly for using pure states. So the solid lines are the neural network results. And here we've just varied the amount of noise on the measurement results and calculated the average fidelity. Red here is for the neural network when using the neural network, and green is when using the sort of standard Stokes reconstruction method of calculating the density matrix. And then as we go down to zero noise, here zoomed in on the inset, Stokes reconstruction overlaps with our neural network results and approaches unity fidelity. And interestingly, perhaps, and this is the last thing I want to mention, is I said we wanted to try to reduce the classical computational overhead in these kinds of systems, right? So what we did was try to see if the neural network system would still work if we threw away some of those 36 measurements, right? So here we have our number of tomography measurements on the x-axis. 36 is the normal amount that you use. And then again, on the y-axis is average fidelity. Here in green, we have our Stokes reconstruction results. If you just use the standard Stokes reconstruction method, when throwing away measurements, going all the way down to just using 4 of the measurement outcomes and throwing away the other 32. And then the red and blue are when we use our neural network. And so you can see pretty nicely when you go down to even just using 16 measurement outcomes and throwing away 20 of them, we still have above 90% fidelity. So this, we're hopeful we can improve when we go to larger dimensional quantum systems beyond just 2 dimensions, right? Beyond just a bipartite entangled state, that we can throw away a relatively large number, or maybe even just 50% of the measurements, and therefore help reduce the classical computational overhead in these larger dimensional systems. And so I think I planned to end 5 minutes before the 45 minutes for questions. So I'm pretty nicely on target here. So I will end with acknowledgements and thank, most importantly, the folks that were involved in all of this work here. The Tulane supercomputer team, which we ran some of the results on, or some of the systems on, and then acknowledge funding from the Office of Naval Research, Northrop Grumman, the state of Louisiana, and the Army Research Office, and also our collaborators at LSU for performing the single photon experiment, which turned out very lovely. So with that, I will end and say thank you very much. And if you have any questions, I'm happy to take them.
Thank you, Professor Glasser, for such a wonderful talk. So we are now open for questions. So please ask your questions if there are any. Okay, I had a couple of questions actually. The first one is regarding comparison with adaptive optics actually. So in your system, you don't have you're not using adaptive optics, right? So in case of how do you dynamically, how does the dynamic performance of the neural network trained system compare to an adaptive optics system?
Yeah, so that's a really good question. Let me just go back here a little bit. So I specifically didn't compare it to adaptive optics because I don't really see this as necessarily something that would compete with adaptive optics, but really as something that can be used in conjunction with adaptive optics. So, this is nice in the fact that it doesn't require adaptive optics is nice because, there's no time involved in this. And what I mean by that is the neural network, right? You can effectively send in images as fast as you'd like into the neural network and it will do its job, right? Generate and then classify as fast as your computer basically can do it, right? So whereas why I say that doesn't matter with respect to time is because when you have adaptive optics, you need your actual adaptive optics to be relatively fast in order to correct for, turbulence. Like if you're coupling into a fiber, you need to have your beam steering be at least as fast as the turbulence is affecting your mode profile, right? In order to maintain your nice fiber coupling efficiency. Here, yes, this all happens on a much faster time scale, but or can happen on a much faster time scale at least. But I personally, I see no reason why you couldn't combine this kind of system with adaptive optics to try to make the best possible receiver, and you can make the best of both worlds.
Okay. We have a couple more questions. So the first question is from Tania Sharma. She's asking, for heralded single photon, will the GNN affect entanglement?
That's an excellent question. We did not look into that. We only did the feedback. Where are we at here? We only did the feedback system measurement, feedback system experiment, which that would affect the entanglement, because then you're effectively pre-correcting for the turbulent propagation. So the photons, you know, that the feedback system would allow you to overcome entanglement degradation. Very similarly, I believe, actually, to an experiment that Professor Forbes did in the past with single photons. The GNN, though, that you asked about, I'm not convinced that that would recover any entanglement, because the generated mode profile is really generated by the neural network. So it's not actually what you detect, right? So I'm not sure that you would be able to, for example, recover any kind of degraded entanglement or non-classical resources when using the GNN system. But that's an excellent question.
Thank you. The next question is from Professor Gautam Samanta. He's asking, in SLM, are you adding the phase correction and combining with the input state, or the SLM is creating the state along with the phase correction?
It's both at the same time. So it's the feedback system, I guess. Where are we at here? Sorry. So for example, here, this first spatial light modulator initially serves to we put a phase mask on it in order to generate the spatial mode profile that we want to send through the turbulence, which the turbulence is simulated on the second spatial light modulator. But then after we generate the correction phase mask, we put a correcting phase mask on the first spatial light modulator, such that it generates an image here that is different from the initial image that was generated by that first spatial light modulator. So it's really both. It's really just a new image that you're generating, but it's a different image than what you initially intended to receive, because once this new image goes through the turbulence, its resultant distorted image effectively is a cleaner image. Does that hopefully answer the question? I hope.
I guess so. So the next question is from Shrestha Biswas. She's asking, will this machine learning work for dissipative turbulence?
That's also a very good question. I think that the answer is yes, specifically with the generative neural network. Let's see here. Because here we have the signal to noise ratio decreasing as we go to the right here. And generative neural networks in general, the reason I say I suspect that it will work for that is because generative neural networks have been used in the past for denoising techniques. And that was one of the reasons why we initially looked into that. So, effectively, I think that the question is, asking, as the signal to noise ratio, i.e. the strength of the image, decreases, this still works pretty well. As you can see here, when we even go to the very, low SNR regime as compared to over here, the generated images are effectively the same as in the low signal to noise, or in the high signal to noise ratio case.
Okay. We have another question. I'm sorry, I don't know the name of the person who's asking the question. The question is, can you please comment on why zero padding and no padding results were different for low number of measurements?
Yes. So all right. So the absolute honest answer is we don't know. We asked ourselves that question is there a difference? And we suspected, quite frankly, that there probably wouldn't be a difference, but there was. It's not a, well, at least in the quote high measurement regime, there's not much of a difference. But as you go down to extremely low number of measurements, there is a fairly significant difference. And the honest answer is we really don't know. We really don't know why there's an effect. It might be just due to the training of the networks, because the neural networks used in the zero padding case, it is always takes as input a 6x6 matrix, right? Just you're zero padding some of them in that case. And when you go down to this, the non-zero padded case, for example, for tomography measurements, you do not have a 6x6 matrix as your input. You have a 4 input system, right? It's just a 2x2 matrix. So it's just different, right? So I don't have a good physical explanation as to why it's different. We just were curious as to if it might be, and it turns out it is. So.
Okay. I have one more question. Like, I'm just curious. In the previous slide, if I'm right, your fidelities in the pure states were lower compared to the mixed states, right?
Yes.
What could be a reason for that?
That is another question that we do not have any idea as to why. So we trained them together. We trained them both together, the neural network. So it's the same neural network that is generating both results. And we applied, I guess not on this plot. Well, on this plot. Let's see here. I'm not on this plot. As we varied the amount of noise, this was always true. So we don't know why, which is kind of strange. But we were only in this case simulating one kind of noise, and maybe that's the answer. The noise that we're simulating is just a rotation of the density matrix by some amount, and all of the elements of the density matrix that we simulate are rotated by the same amount, and so maybe that affects the mixed states in a different manner than the pure states. And so if we simulated different kinds of noises, maybe the results might even switch. I'm not entirely sure, but I suspect it has to do with the way we added the noise.
Okay. We have one more question from Professor R.P. Singh. He would like to ask it himself.
Yeah, thank you for such a nice talk, Ria. So wanted to know, have you done any calculations? Suppose you want to do satellite-based quantum communication, and then you apply this machine learning along with adaptive optics. So can you reduce the size of telescope, this ground station? That's very important parameter, the size of telescope. Suppose we reduce it to 35 centimeters. Then life becomes much easier instead of going for 1 meter telescope. So have you done any kind of calculation, like for better signal to noise ratio? Suppose you are having LEO satellite, 700 kilometers or 500 kilometers. What will be the size of the telescope, minimum telescope size, when you combine adaptive optics along with your machine learning?
So that is a fantastic idea. We have not looked into that at all, and hadn't even thought to do that, to be quite frank. So that is an excellent.
But that
idea.
will be very nice project if you can do that.
That is a wonderful idea.
We'll be certainly interested into that if you can do that.
Yeah, that honestly, we just had not even thought about that, and that is a great idea, because I suspect that that might very well be a good application of this. Yeah.
Okay, thank you.
That's excellent. We should discuss.
We'll
that
be looking
later,
forward to work with you on this subject if you can help us in that.
Yes, absolutely. We would be more than happy to. Yeah, definitely. We should keep in touch about that. That's a fantastic idea.
Thank you.
Okay, maybe I will stop sharing my screen now, I guess. probably?
Yes. I would just like to thank you, Professor Glasser, one more for being there at such an odd time from where you are. So it's really early in the morning, but thank you for joining us live. We really appreciate it.
Thank you so much. I really appreciate the opportunity.
So thank you all the speakers, Ravi, Abhinandan, and Professor Glasser for being there in this session. So this was the last session of Scope 2020. Thank you so much to all the speakers who were there and the poster presenters who were there today. I would now call upon Ayan, who is the chair of the conference, and for the closing ceremonies.
Thank you, Anindo. Once again, I would like to thank all the participants and speakers from various parts of the world, and also the attendees who have attended this scope. And first of all, again, I'd especially like to thank our basically the team behind who are hosting this conference, Anirban, Bimlesh, and Shomya. And also, I'd like to thank JK for maintaining a smooth and streaming in YouTube. So without speaking much, basically this session is for taking the feedbacks from participants and attendees, and the feedbacks regarding what all the things that we can do or we should have done to improve this conference, and also what all the things that we should not have done to in this conference. So this session is for that. So we are open to answer your question or your feedback regarding this conference. So I mean, anybody, if anyone has any queries, they can raise your hands, or they can post in chat, or they can simply unmute their mic and can tell to us. We would be happy to answer them. Okay, I would like all the team members to please come on live. I mean, please just turn on their cameras.
RP sir has some comments.
Okay. Yes, sir.
Yeah, like every year, my feedback is like every year I request there should be more questions from students, but I don't see not many questions coming from students. And as I commented, being chair of the session, you should be able to ask questions. Very little questions were coming from students. And I am requesting every year that you should ask questions. This is the conference by the students for the students. So unless until you ask questions, you are not going to learn much. You should be ready to ask questions. That's what.
Okay. Thank you, sir. I mean, from next time we'll definitely ask more questions.
Yeah. So it was really very nicely organized. I enjoyed. Yeah, certainly.
Thank you, sir.
Can we have some comments from Gautam sir?
Yes.
Oh, it's excellent. I should say that one. It's such a short notice. The way students, our team, Scope team made things work, and the way it was performed, it was fantastic. So I didn't really expect better than this, what you guys have done. So I really appreciate the way the whole team worked together and made it. Even though we expected, more number of students from different parts of India, to be part of this conference, but you cannot really help if the students don't come. You cannot really help. So that's something we don't have any control, or the student conference team has no control on it. Or the questions means, as Professor Arpi Singh was saying, that when questions should be asked from the students, but that we always encourage. But if students don't ask, you can really just help. So it's not the fault of the committee, those who are conducting or making things. They are just putting their best effort or hard work to make this kind of conference running. But as it is a really a good suggestion, and means Professor Arpi Singh always gives that kind of suggestion to improve, and the students should really ask questions. So that I also believe. So beside that, I don't have any comment. I am really happy that you made it, and because this pandemic situation was there, and then we are afraid that perhaps this year we might not be conducting this conference, and we are not really in the mood of discontinuing, because once you discontinue, then starting it again is a big setback will be there. So then the entire team worked together and made this event successful. And the webinar, sometimes people don't know, perhaps just a live conference or in-person conference is something where you can interact, and then there are fun moments also, and so there's a good food will be there also. So those things are there, but due to some limitation or other, like funding, you might not be really getting many more faculties or speakers from different parts of the world. But due to this webinar, somehow we somehow managed good speakers and the leading scientists talking. And I thought that is another opportunity, even though, because any problem comes, you try to find out the opportunity from there. So in this webinar, even though the corona forced us to not to spend money or bring people to PRL and have fun, but that also at the same time gave that opportunity to listen others, those who are sitting outside, means outside India or different parts of India, and they made interesting talks about their research. And that's somewhere it is also good. So in future, I don't know whether Scope team will consider this webinar mode to continue or the in-person conference. So that's up to the next chairman, because we are definitely going to continue this conference. Perhaps next year we will continue, and then years to come it will continue like the way it is now a standard conference now at this moment. So perhaps you can consider in some way that live next time, just keeping some sessions live or recording that one, or then making it live, so that so people can just make also a talk from without visiting PRL. So that kind of option, perhaps having the experience you guys gain, perhaps that can be used in future, and that can be used, and then we can strengthen this conference or take this conference to a next level. So you asked me to talk, and then I started giving a speech. So I stop here, and I will not tell anything. Thank you.
Thank you,
So
sir.
I would like to compliment the students. They have done a wonderful job, because I attended this OSA meeting, Quantum 2.0, this laser science FIO. It was like organization was nowhere like less than OSA, like such a big organization, quality wise, management, time management. And although I asked students to ask more questions, but you should be happy that we have, like all of you, or we have asked more questions for each talk than the OSA meeting. I was attending the talks there. Hardly one or two questions were coming to very big shots speakers. But here we were able to ask a couple of questions from most of the speakers. So that way you were asking questions, but more questions is always better. So it becomes more lively. So I must really compliment you guys. Fantastic job you have done. Nowhere like international standards. Okay. Thank you, guys.
Thank you, sir.
I don't know if there is any more feedback from the participants, but what I think all the committee members should be live, and then we should take a snapshot or a print screen,
yes.
so that we can just put that one in next year's, means that can be the flyer for next.
There are 24 participants. They are not speaking. Yaar, why? None of them. I see 24 guys there, but none of them are speaking other than Ayan. Why? Gata? They're scared of you?
आप डरा रहे हो, आप डर, you are scaring.
कौन डरा रहा मुझे पता नहीं, तुम डरा रहे कि मैं डरा रहा. Okay.
Okay, so I think we should have a snap so that that's a virtual snap, so that we can take this one for the advertisement of Scope 2021. Who is going to take that? Who is the expert of Anirvan in California, San Francisco? He is in San Francisco.
Yeah, how everybody will come on the screen? I don't see still. Ryan is also there.
Where is Ravi?
Adi, yeah.
Yeah, I think Vardhan, Nijil, Pranav, they don't have a camera. Like Nijil is there.
I can see Nijil, yes.
Yeah.
Nijil is there. Subit is there.
Yes, sir, today no camera.
No camera. I think we can add this photograph later on. We can edit.
So, Madhu is not there.
Madhu, where is Madhu? Okay, we have to edit that photograph. So can you guys quickly take a snap and then we add what happened? So your video cannot be recorded. Please, Sandeep.
I have taken a couple of snapshots. So.
Oh, that's great. That's great.
Even Ananya is there, Ravi's daughter.
Ravi is there, yeah, Ananya. Great.
She just got up and she wants to be with me now.
Okay, so it's like the chair's call, when to end.
Okay, so thank you all. So now we can
enjoy
this conference. Yeah.
Okay, great.
Okay.
Thank you.
Thank you very much.
Thank you, guys.
Bye.
Thank
Bye.
you. Bye.
Thank you so much.
Great job. Thanks.
Excellent.